is one of our, like, not the last day, but one of our last days, and we're going to come to an end somehow. So today and tomorrow we're going to address some totally different topics. You already learned a lot about like phase contrast, diffraction contrast imaging with a parallel beam on our sample. And today I'm going to present you the scanning technique, which means that we have a very fine electron probe instead of having a parallel beam. We just raster scan that across our sample. So here's already a very beautiful example how those images might look like. So this is an HRTM image that you somehow got to know yesterday. Here you already see that there is some misalignment of the crystal. So this is not a clear image, isn't it? Where like the atomic columns are, as you know, it's a little challenging. There is as well some delocalization effects because this is non-aberration corrected HRTM image. We see those fringes of our diffracted beams which don't superimpose right in this area where our like crystal is. This is just a nanoparticle on a ceramic support film. And here on the right hand side, this is the direct comparison to an atomically resolving HR scan image. So high resolution scanning transmission electron micrograph. And so this is a dark field image on the left hand side, so the whole image is dark. And the rest, like where the atomic columns are, you see some contrast. And in this particular case, you can directly relate the local intensity to the local position of the atomic columns. I mean, this is the beauty of the technique. I'm not only going to talk about atomic resolution scanning, but I mean, you can do a lot of studies in lower magnification, but this is just a direct comparison, which I wanted to start with, so that you get some idea that there is, like, let's say, a huge difference between this parallel illumination mode and this raster scanning. And so let's come to the very early part. So I'm going to present you some information about the scanning procedure because there are some fundamental differences between a scanning electron microscope and our transmission electron microscope. So the scanning is more elaborated. I'm going to talk a little bit about the fundamental or the critical basics behind C contrast imaging, like the similar, let's say, to backscattered electron imaging. It's very powerful to gain some direct insight into the like local chemistry of the material. It's not only about like any diffraction contrast. And I will spend the last third about aberration correction, so just to demonstrate you like the modern capabilities of modern microscopes. So what does it mean? I mean, you already saw a very similar picture in our Siegen lecture, isn't it, that we have a very fine electron probe on our sample. In this particular case, our incident beam energy is far higher than the scanning electron microscope. So we are on the order of, like, let's say 60 to 300 kilo electron volts with modern microscopes. What you can already see here is that we cover a certain angular range underneath our sample with different detectors. So we collect intensity, which is scattered or which is diffracted due to the interaction of our incident electron beam with our sample here. And there are different ways. So most microscopes, they come with a so-called HAADF detector, which means high angle. This is written here, high angle. This is large scattering angles. High angle, annular. Annular means it's a round detector. Dark field detector. Dark field because it's not the not the direct beam in the center that we collect, but we collect signals which are scattered into far, into a very large or far angular range. Okay, and this is what commonly provides chemical contrast. Closer to our direct beam, we have a so-called just annular dark field detector. This is the detector with which you can also observe diffraction contrast, because as you will see, I mean, we are working, or we currently work in diffraction mode, meaning we don't work in any kind of imaging mode, so we just image our backfocal plane onto these detectors far below the projection direct beam or some of these scattered reflections on the detector. If you do so, if you record those diffracted beams, and you connect those with the detector, I mean, you will definitely end up with some diffraction contrast, because we know that the excitation of those diffracted beams and the intensity depends on the structure factor, it depends on the orientation of our crystal, and so we end up with some diffraction contrast. So we would see lattice defects, we would see different grains, different orientations of grains. Using just a larger angular range, those contrast contributions would somehow vanish to a certain extent, so that we end up with this pure C contrast. Then we might use a bright field detector, and as you will see, in particular to detect light elements in atomic resolution STEM imaging, the bright field detector plays a crucial role, because as you know, the atomic scattering factor into large angles is like far larger for heavy elements, so it's always easy with this C contrast imaging, so using this Hadoff detector, it's far easier to detect the distribution of heavy elements, not of very light elements. So for light elements, it's more scattering in forward direction than into larger angles. So this is why we also need a bright field detector. This is how a detector looks like. In principle, most of those detectors, in particular if you have a very sensitive detector, you have an active area of the detector, and on this area you just have some scintillator material that converts our electron beam into a light signal, which is covered out of the microscope, and by using a Hall multiplier, just this signal, this optical signal, is amplified. So this is just a Newton detector, like angular detector that covers this range here, and just in the center of a hole. So this is a dark field detector. Here are several detectors inserted in the microscope. They just sit in at different depth of the microscope. Slightly, they are either inserted just from one mechanical drive, or you might have several drives to insert those detectors. This is bright in the center, an angular dark field. In this particular case, the high angular dark field detector is even segmented. This is for very special techniques where your electron beam is deflected, for instance, due to like electrical fields within the sample. Nowadays we can measure electrical and magnetic fields down on the atomic scale. So this is a very elaborated technique already. This is just a comparison between the bright field TM image. This is just diffraction contrast using an aperture at 200 kV, and this is the bright field scanning TM image. And as you can already see, you know these pictures, as you can already see, there are certain similarities. So the hole is bright in those cases. We can end up with some faint diffraction or some pronounced diffraction contrast here, which we're interested in the layer of this solar cell. And there's a certain so-called principle of reciprocity. And I mean, in this particular case, we have a parallel beam, and in our backfocal plane, we have a focused reflections, isn't it, for a perfect parallel beam in conventional TM imaging. Here it's just the other way around. So I mean, here we have very fine and focused electron probe, and we get a large angle, let's say, in our reciprocal space. So this is somehow inverted, and I'm not going to go into the details here, but in principle, there are many similarities, like regarding image contrast. And so with bright field and dark field STEM detectors, we always end up with some pronounced diffraction contrast, and only with this HA-PF detector, we just have a pure, almost pure chemical contrast. This is the difference in scanning. So in the scanning electron microscope, we just deflect the beam, you know. And for large fields of view, the local angle of impact on the surface changes. I mean, we just raster scan this beam, and only in the very center of our image, we have a perpendicular impact on the surface, and as we go further, let's say we have a scan field of 1 millimeter, this angle is already pretty large. Meaning that the path of our electron, just imagine a thin sample, and if you do so in a scanning electron microscope, the path length through the sample becomes larger for larger scan fields, isn't it? I mean, this is simple geometry. We don't want to have that in our transmission electron microscope. In our transmission electron microscope, so this is our sample, what we want to have is an electron beam that always hits our sample under 90 degrees. Meaning that this path through the sample is always of the same length for a plane parallel sample, okay? Because this is beneficial for spectroscopic analysis. Because I mean, just imagine that this path length changes, secondary processes like absorption, yes, and fluorescence might change, and you have to compensate for that. Probably not knowing about your path length, and even for heliums, it's beneficial to have like the same path length through a plane parallel sample. This is realized by just putting like this pivot point of the scanning system, meaning our scan coils, just right at the back focal plane of our objective lens. You can easily imagine if you tilt, like let's say in reciprocal space, you know your lens, this is a parallel beam here in the back focal plane of our objective. And what happens, this is just, let's say, this is the back focal plane, this is our like incoming light, so to say. And what happens here, this is just the focal distance of our lens, it just focuses the beam here, and even for the refracted beams, it just focuses here. This is just light optics. And this holds for every measuring point. I mean, I would say for scan fields below 1 by 1 micron. So for very large scan fields, this is not realized that perfectly anymore. But in principle, we want to have, I mean, a perpendicular beam in all measuring points in our sample. In modern microscopes, I mean, older microscopes, this beam was not, you know, like, I mean, we have this scanning, and for modern microscopes, we even have a de-scanning system. So we have a second set of scan coils below our objective lens to put our diffraction pattern back onto the optical axis. This is in principle needed if you want to do spectroscopy, because with spectroscopy you want to collect that signal using the heat spectrometer, and we are going to deal with that tomorrow. Otherwise, this diffraction pattern would slightly move. This is what you will see at our transmission electron microscope that we have available here, so the diffraction pattern slightly moves. And low magnification for large scan fields, it moves quite far, and it might even hit our dark field detector, meaning that our central direct beam might hit our detector as it moves, so which is not very good. We want to have a static diffraction pattern down here while we are scanning there. So this is why you need symmetrical arrangement, or I would say it's beneficial to have that. There's one slide about the probe size, because we already talked intensively about the probe size of our electron beam. And this is just like, let's say, a conclusion about. We already learned that the diameter of our probe depends on our diffraction error, our spherical aberration, and the chromatic aberration. In the scanning electron microscope, we had to deal with the chromatic aberration, because at lower landing energies, that clearly caused the broadening of our beam. This formula was already presented in the SEM lecture. But this is exactly, in principle, the same for the transmission electron microscope. I mean, we have our spherical aberration, we have our chromatic aberration. E is far larger. Delta E for, let's say, shot diameter is the same. But in principle, this is the curve that shows the size of our electron probe on our sample, depending on the probe semi-angle, which is like the opening angle of our electron probe. There's an optimum. This is a non-aberration corrected microscope here on the left-hand side with a certain CC value and already pretty good objective lens. And the probe size here is of the order of, let's say, 5, 4, 3. This is 1 angstrom, 2 angstrom, 3 angstrom, roughly. So this is what we achieve just at an optimal angle here of roughly 10 milliradian for 200 kV. So 300 kV is a little bit better, but in principle these are our optimal parameters, and this is what is like also the capability of the installed microscope here. So we can do atomic resolution scan imaging with a certain resolution of, let's say, 2.5. 2.5 angstroms. With the CS corrector, we already learned about the CS corrector yesterday. We can use the same, like electron optical system. Instead of in the imaging system, we would just put it in our illumination system. So to compensate for the CS of our objective lens, to find an even finer probe on the sample. It's just to form a smaller probe on the sample with a higher curve for atomic resolution, imaging and spectroscopy. And this is the curve for a microscope with a very small value of CS, just by compensating or correcting for this value of the objective lens. And here you can see that the probe is even smaller, so we get down to, let's say, 50 picometers or so, which is, let's say, smaller by a factor of 6 or 5, by having even a larger semi-angle, by allowing for a larger semi-angle of our probe. So here we have 10 million, here we have 25, there's a factor of 2.5, but a factor of 2.5 gives us a higher current by a factor of, let's say, 8 to 10. Because just assuming that the current is constant and we just cut with the aperture, larger. It's the area of the aperture which is larger, let's say, by a factor of 7 to 10. So we have a current which is higher by a factor of 10 and a smaller probe which is smaller by a factor of 6. So this gives you a higher current density by a factor of 50 or so. And this allows for atomic resolution imaging on a daily basis. Nowadays. So let's just have a look what happens if you use an aperture that is too small. So this is the shape of our electron probe. This is the angstrom scale, so this is roughly, let's say, 2 angstrom for a non-corrected microscope. And if you use larger apertures, so just to go up this curve here, you will see that the probe shape, so the loop gets broadened, the current the overall current might be a little bit higher, but it gets broadened. But even for smaller apertures here, one might think about that you could enhance the size of your probe by just using a smaller aperture. But due to the diffraction error at the aperture, we even get a broader probe. So it doesn't make sense to go to smaller apertures to gain resolution. So there's one optimal aperture for each of the microscopes that depends on the energy. That in principle does not that much depend on the energy because this is like for the energy is constant, but in principle, like there's one optimal aperture. If you don't rely on the best resolution of the microscope, but you need higher current for spectroscopy, I think you can always use a larger aperture. But in principle, just for imaging, there's one optimal. So let's have a look what we see in our microscope, just to do some alignment in STEM mode. Some of you already attended the lab course yesterday, and we did finally we did some STEM imaging of our aluminum sample already. We even tried atomic resolution imaging, but unfortunately the sample turned out that it's a little bit contaminated. So this is what you see in your microscope on your viewing screen, in principle. It's the shadow image of our sample. So this is the central disk. It's like a seabed disk on our screen because we are in diffraction mode. We provide a probe with a certain convergence angle. So we see a disk in our diffraction or a diffraction pattern consisting of disks. Depending on the size of the disk, depends on the size of our aperture that we use. And here it's already defocused, and you see, in principle, this is the shadow image of an amorphous sample. So you just see some contrast in the center here, which just looks like a TM image, like a TM image in parallel illumination mode of an amorphous material. And there's some weird contrast around, some streaking and some lines going around and speaking. And this is due to the aberrations of the microscope. And I would just like to demonstrate how that looks for another lens with a very poor quality, huge aberrations. This is just a glass of water that magnifies the wall paper behind it. And you see in the center that this is a magnified image of the structure of the wall, so it magnifies. But in these outer regions here, we have huge aberrations. And you already see these distortions here, and somehow infinite magnification of the structure behind. And this is just due to these aberrations of this glass filled with water. And this is somehow very similar because, I mean, in the center, we have a clear shadow image, and around we get some weird contrast, which we don't want to have. And you just have to imagine that now your electron probe in this particular region, so all this is the intensity distribution of your electron probe, which is not focused on your sample. So the electron probe is above or underneath your sample, and you will see, let's say on this slide, how this shadow image works. So, first of all, I would like to emphasize that you can make use of this shadow image because you can use it to align your stem mode. The so-called bronchogram is commonly used to either record it with a CCD camera continuously, or you just watch it using the small screen or the large screen, and then you can do all the alignments that you need for a perfect beam alignment. And in principle, a perfect beam alignment means that your electron beam propagates parallel to the optical axis. It hits your sample under, let's say, 90 degrees, so it's not tilted, all those things. Meaning after the gun alignment, you do a proper condenser alignment, and finally you adjust the sample height, you focus your probe onto your sample. One major aspect will be to select the right aperture and to center that around your probe, because we want to cut off the tail. What you see here, these outer areas, this is just the tail of the probe that we don't want to have because we want to define our probe on the sample. And this is, in principle, this is it. And it takes, let's say, to switch from tier mode to stem mode, if you already have a pretty good pre-alignment, you would do like some of the condenser alignment in tier mode and then to switch to stem mode. In principle, it shouldn't take longer than, let's say, 5 minutes or so. This is pretty convenient. You can switch back and forth even with older microscopes. So, with this so-called bronchogram for non-aberration corrected microscope, we can do, I would say, the most accurate alignment of our probe for the best resolution. It's easy to find the optical axis because what you can do just for aligning our electron beam parallel to the optical axis, you can just shift your probe up and down, just by changing the focus of our objective lens. And by that you will see whether your sample moves or not. Because if your probe just moves up and down parallel to the optical axis, then your shadow image does not move, it just gets enlarged, or demagnified. But in principle, if our electron probe is inclined to the optical axis, then it would move up and down in a certain direction, meaning that your shadow image would move by just focusing and defocusing our sample. And so you can use that to find the optical axis, even to correct for the two-fold astigmatism of our probe, because we want to have a round-shaped probe. We don't want to have an elliptical probe on our sample. All that can be done using the bronchogram. This is pretty convenient. We currently start with a large aperture, because then we see all that, and you have to find the center of your bronchogram. And if you are strongly defocused, or your sample might not be, let's say, amorphous or so, then that helps a lot to start with a large aperture, so that your field of view, or the shadow image, becomes large. So simply that you see more. And I mean, there's one further aspect. It helps a lot if you have, let's say, an amorphous region of your sample to do the alignment. In many cases, even for crystalline materials, at the edges of a TM sample, you can't find at least 1 nanometer or 2 nanometers of an amorphous region. This is sufficient to align your electron probe. If you don't have that, I would just put my electron probe somewhere in a very thin area of your sample, and after a certain period of time, almost any kind of material gets damaged, meaning that you just generate your amorphous area by yourself, just by destroying your sample to some extent. It's on the nanometer scale, so it should make any. And this is how this shadow image forms. So we have in this particular case, we have a structure. This is like just a light optical consistent, another glass, and the black and darkness is etched in a room. And you see this dark light here, that, or this bright, higher intensity here that evolves, just propagate through our lens, as you can see it here. And we have a certain mirror symmetry of our image. So what you see is that the light that propagates from here, it ends there on the left hand, on the upper side, and the dark here. So this is just an inversion that happens with such a lens. And in these outer areas, we again see this. Here we see an image. So this is not inverted, and in these outer areas here, we get some inverted contrast due to these lens aberrations. And the same happens here. In principle, we have our electron beam, our lens. So this is our electron beam, which is not focused very well. These are all the electron paths that we accept by our aperture. And we know that we have spherical aberration. The spherical aberration, in this particular case, again means that rays very close to the optical axis here, these ones, they have a certain focal length, but all these rays far from the optical axis, they feel a stronger impact by the lens, meaning that the focal length is shorter. And if you now follow all these trajectories of our electrons, then you will see that for, let's say, for these outer rays, this is a slightly defocused probe. In principle, this is your inner part of the probe. It's just these inner rays here that contribute, and all the others, this is what you want to cut off. This is just the tail. But if you follow this, the electron rays that pass through the sample, what you will see is that from here to there, and from here to there, that you get some inversion of the image. So the image here on the screen, if you slightly under focus our probe, meaning that the strength of the lens is low, then you end up with an inversion here. But in these outer regions, just follow these rays, they just propagate into our backfocus plane. For these outer rays, the image is not inverted. In this particular case, for an underfocused probe. So the inner part is inverted of our shadow image, while the outer regions are not inverted. And this is what causes this weird contrast in between here. If you overfocus our probe, so if you shift the probe up above our sample and we focus our probe here, then there would not be any inversion. So you wouldn't see these rings for an overfocused probe. So when you go from under to overfocus, what you will see is, at least for your inner region of your sample, that you get an inversion, or we have mirror symmetry. It's an inversion of the whole image simply due to geometry. And the closer you get to focus, the larger will be the magnification of our innermost region of the sample. So here we have a finite magnification of this inner region of our sample, depending on this distance of this, let's say, focus probe to our sample. And the closer you get, remember that our probe is of the order of a few angstrom. If you focus this very fine inner region of a probe onto your sample, just assume that it's only 1 angstrom for a probe corrected microscope, then what you will see is just this inner region of your electron probe, or this inner part, will just hit a single atomic column. And how does the shadow image of such a very small area look like? Because there's hardly any contrast anymore because we don't observe such features. This is gold particles and so on, it's important to see clear shadow image. This is how it looks like if you focus well on your sample. So you end up with an almost infinite magnification in this inner region of your sample. This is well focused here now, but these outer regions here still show the sample as a finite magnification. Okay? And this is, in principle, I would say a perfectly aligned probe already. And what we have to do now is to just cut all of this, the tail of the electron probe, just by using a small aperture that just covers this inner region. This is what you do. So first of all, you align your microscope under those conditions, so with a slightly, let's say, slightly defocused probe, you can get closer and closer. You align your astigmatism and all that, and your rotation center, so meaning making your beam parallel to the optical axis. And finally, you just focus, you cut off the tail, and then you are already focused on the sample, and immediately records that image. And for sure, if you move the sample around, the height of your sample, then you will either have to adapt and adapt the C height of the sample, or you will have to refocus onto your sample. But as long as you stay to the same area, you might need to align astigmatism if your sample slightly changes. You might need to compensate for that after a certain period of time. But in principle, this is how we align the stem model. This is how astigmatism looks like. So this is a perfectly aligned probe. This is still not focused here, but just to demonstrate how the astigmatism looks like. So the worst that astigmatism gets, you will see some streaking here in a certain asymmetry. So this is already elliptical. If astigmatism is severe, this ellipse will be pretty pronounced, you know. But in principle, this is just some, let's say, minor astigmatism, so you will see some streaking. Meaning that in one direction, your probe is already focused well, but in the other one, you end up with a finite magnification of your structure. You can just use that, you will see that the streaking changes by changing the stigmators of your microscope. And here you have to use the condenser stigmator, because it's your illumination system of your tool. It's not the objective stigmator in this particular case. So it's only the condenser stigmator to make the beam ground on your sample. And you can nicely see that, and this is what we did as well yesterday. And yeah, so after aligning the astigmatism, you get to focus your electron probe, and finally you just insert one suited condenser aperture and just cut off the tail.
There are some features in this slide. There is some feature is something like something is focused, but in the right image that you are saying it is focusing immediately. Looking like feature.
You mean that there are some features?
Yeah, it is. In my opinion, it is looking like left, but there is a
more focus.
No, because here you still see this is an amorphous sample here. So you see some contrast. This is your amorphous sample at finite magnification. And here, I mean, this is even higher magnification. So you want to achieve the highest magnification on your sample, meaning that the probe gets focused on your sample. I mean, in best case, but this only holds for very, very fine electron probes, you hardly see any contrast features anymore. So if you have like a 50 picometer electron probe in an aberration corrected microscope, the probe is so small that whenever you hit like either an atomic column or just in between, you know, there are no features because there are no differences in the local, or hardly any differences in the local potential of your sample that affect, you know, these like intensity variations. So there are hardly any intensity variations. I mean, let me just go here. This is how an aberration corrected electron probe looks like. We're going to come to that later. I just want to share that here. This is an aberration corrected probe, and instead of having just 10 milliradian in 200 kV, this is already roughly 50 milliradian. So it's a far larger probe, and you see that there is no contrast at all upon like focusing the probe on the sample. Because in this region here, where you have this extremely fine electron probe, you know, you end up with an infinite magnification of this very small sample area in this shadow image. So this is a probe corrected probe. Let me just come to this slide, because I would like to address which signals we record with our detectors. Because I mean, there's a lot going on. This is a diffraction pattern and so on axis, so this is a sample probably for atomic resolution imaging, so you would also have to deal with the alignment and the orientation of your crystalline lattice with respect to the incoming electron. and why you are able to record an HRT image even with a certain misalignment of a few degree, let's say up to probably 2 or 3 degrees, you will end up with a crystal that is on fringe image. You will hardly achieve that with good contrast in stem mode, because you can imagine that your electron probe, it has to propagate along this atomic column or your atomic planes, and you have to hit them almost perfectly. So however, like this alignment of half a degree or so already leads to a worse contrast, so to reduce intensity variations in your atomic resolution pattern. And what you can do, in particular for high-angle angular dark-field imaging, where you want to achieve C contrast, you just cover a very large scattering angles, like is shown here. So this is the diffraction pattern. These are your inner reflections. To collect those reflections would cause like some bragg contrast in your image. You have the bright field detector to cover this one, but for HA, EF, we just cover these very large scattering angles. And the reason for this is, as you can imagine, scattering into large angles goes with a roughly C to the power of 2. This is what we already learned. Meaning that for these larger angles, you only get some dependency of your scattered signals on your atomic number to the power of roughly 2. And so we can minimize this effect of the zero-order Laue zone of these Bragg reflections. And there is just a rule of thumb that I would say 5 times or 3 to 5 times our Bragg angle. This is the inner acceptance angle of our stem detector, of our HA detector for this C contrast imaging. So let's have a look how such images look like, just for different materials, so that you get some pixel after line of probe. You can activate this raster scanning. You can set the dwell time like in the scanning electron microscope, and just for search and focusing and all that stuff, you just use a short dwell time. For data acquisition, you might use like a prolonged dwell time in each measurement. There are different ways. For instance, if the sample drifts, you might just record your frame with a very short dwell time, do some drift correction, and just record and integrate those. I mean, all the scan modes that you have available in the scanning electron microscope are available in the transmission electron microscope. And let's have a look how those images look like. This is a very, let's say, simple example of titanium oxide, tantalum oxide nanotubes. So those nanotubes are grown by electrochemical etching into a substrate. And this is already C contrast imaging. And you see the original substrate consists of titanium and tantalum heterostructure. And so the material was etched finally. And these are the tubes that you see. And those tubes are round. And in projection, what we see is a certain mass thickness. So the thicker the material in this particular region, for this tantalum oxide, for instance, the thicker in projection the material is, the higher is the contrast. So there is a certain, intuitive interpretation to that, although we don't go into the details about quantification, but in principle, the thicker the material is, up to a certain thickness, your signal will almost linearly increase. There's a hole up there, so we don't scatter to these large angles here. And you can directly see that there's a chemical contrast between the tantalum oxide and in between this titanium oxide, simply due to chemistry. Because the titanium is far lighter than the tantalum, and this causes this stripe contrast in this direction. From the right to the left, you already see that the sample gets thicker. So the sample is thicker here than there, because the intensity is far higher, meaning as I mentioned, the higher the thickness, the higher will be the signal towards this scattering. This is simply due to the increasing probability of scattering. There's another example. This is just a multilayer structure of tungsten, and like a very lightweight material, a very heavy material. On the right-hand side, there is an HRTM image. Just for comparison, you have a substrate here, a light substrate, a lightweight substrate. The tungsten appears dark here because of the conventional TM due to Bragg contrast and due to this very heavy atomic number, the scattering probability is higher, and this very light interlayers appear bright. In C contrast imaging, there is an inversion of the contrast because we need the atoms to scatter to these large angles. This is why the substrate is dark and there is some hole which is dark too. Contrast might be a little bit too high in this image here. The reason why I would like to share this, the question of this project was to measure the spacing of these layers. So these are Bragg mirrors for X-ray optics for, let's say, the wavelength of the regime. And to measure that just by high resolution TM or conventional TM might be a little bit challenging because whenever you defocus, it depends on your focus, you know, it's pretty challenging to measure those distances very precisely. Here you can get some Fresnel fringes, so this is this dark and bright contours here, just about this bright contour here, just upon some defocus. But if you go to Gaussian focus, where we don't see, we can hardly determine, you know, the edges or the borders of these different layers. But in STEM imaging, it's quite clear. So we have an electron probe, we get this clear chemical contrast, and based on such a data set, it's far easier to measure just the thickness of such a layer if you have a clear chemical contrast, because the contrast mechanism is totally different. So this is a very, let's say, simple application of STEM imaging at intermediate magnification, just to measure the thicknesses of layers, to get into the local chemistry. I mean, we see the chemical contrast, and by that, people just used this intensity variation across to determine this, like this double layer periodicity. Another advantage of just having a very fine electron probe that we can let's say, focus on our sample is that STEM imaging is in principle far better for very thick samples. And thick means up to, like, let's say, 2 to 3 micrometers or 300 kilo electron volts. We did some analysis of biological specimens like photonic crystals, of butterfly wing scales, and it's far easier because in conventional TM you always end up with Fresnel fringes, in particular of thick samples, and here you just focus your electron probe at a certain depth of your sample. And here are already pretty large decorated silica balls, so these are of the order of a few hundred nanometers. But you can clearly see these decorating metal particles, these nanoparticles. But you have to keep in mind whenever you focus your electron probe, this is already a pretty big structure, and you focus your electron probe, you might either focus it up there or down there. If you focus it to the uppermost particles, you will not see those. I mean, in this particular case, you always have, to a certain extent, you always have some multiple scattering within the material. But in principle, we are able to visualize the distribution of very fine particles, as you can see here, and this is due to the fact that the silica is amorphous, so there is no drag diffraction. And the silica is pretty lightweight compared to these metal particles, so this is also a matter of contrast. But in principle, those particles are the size of only very few nanometers, and you see all these particles on the surface, you know, of these silica spheres, which you would never be able to do by just conventional TM imaging, because you would end up with almost any kind of like Fresnel contrast and the superposition of all these contrast features. You would not be able to distinguish all these different small decorating particles. So, I mean, there are different benefits of doing STEM imaging. This is a pretty, let's say, old example already of a non-aberration corrected atomically resolving image here of a very heavy dopant in silicon carbide. I mean, silicon carbide is pretty lightweight, and these are very heavy dopant atoms, and this is a cluster that is incorporated in the silicon carbide. And I mean, this is from the, let's say, it could probably be from the late 90s, even without aberration correction, you can use such characterization down to the atomic scale. So this was done without aberration. And I mean, such an experiment is always easier if you have a clear chemical contrast. So heavy elements in lightweight matrix, this is always TM, so atomically resolved TM, and STEM imaging. So this is a germanium film on silicon, or the other way, silicon oxide capping layer. And while you hardly see any variation here by HRTM, this is due to the imaging process and the phase shift by the germanium and the silicon, you can clearly see those differences in the STEM image. So you might run into trouble with not seeing a lot in conventional TM imaging. This is a textual film, so there is hardly any diffraction contrast, as the orientation is almost the same. You clearly see such chemical differences in the STEM image using high angle angular ducting. This is convincing, isn't it? So let's come to the atomic resolutions. So you already saw this shadow image. This is far defocused, and as we know, just by compensating for our spherical aberration, we just use this very complex electron optical system to compensate for a positive CS value. And here we want to get CS or very small. And what happens if you focus this electron probe now? In this particular case, you see that we have just a very nice shadow image with a large field of view with this aberration corrected probe. This can be simply understood because CS doesn't affect our shadow image that strongly anymore. And this is the case when you just focus your aberration corrected probe on the sun. Meaning that for all these, what we see is that we are able to accept many more, contributions in towards larger angles through our optical system, through our objective lens. And this is why we are able to, in principle, to realize a far stronger beam with a even smaller size on our sample. And now here, we can just use a larger aperture. We have to keep in mind, this is what you learned during the SEM session. The larger our convergence angle is, the smaller is our depth of field. So our depth of field for such a probe-corrected probe is so small that you can even section your sample so every 2 or 3 nanometers. So there are tomographic techniques where you just focus on top of your sample, you go 3 nanometers down, we put another image, another 3 nanometers down. Just by, you can go through your sample, you will only see a very thin slice of your sample focus or in focus. This is what, how this imaging process works. In principle, we have the distribution of our local potential due to these atomic currents along the zone axis direction, which are very fine. And depending on the size and on the shape of our electron probe, currently it's like first approximation Gaussian-shaped probe with a certain width. This is just the convolution of this measured potential with the shape of our probe. There's nothing else behind. So the smaller the probe, the better is the resolution in our atomically resolving STEM image. So this is what's given here. So the resolution is limited by the probe profile and the probe size. There's one advantage of atomically resolving STEM imaging compared to HRTM imaging. We learned about yesterday that in diffraction contrast imaging, we have a strong impact by our aberration function. The aberration function causes change and inversion of our contrast features. So for Schätzer defocus, we have dark atoms on a brighter background, and if you go down with our defocus, in principle we get a contrast inversion. So we in principle never know where our atomic columns are. Here we don't have that, so we can focus our probe a little bit higher, a little bit lower, and this is the defocus value here on a sample. This is even the convergence angle for an optimal convergence angle of this 10 milliradian, so this is somehow the optimum. But if you go up and down, you will see that there is no contrast inversion. What you see is if you focus your probe above the sample or underneath the sample, for sure the contrast goes down, because we focus a larger probe. And the effective size of our probe becomes larger and larger if you defocus your probe. And this is why the contrast vanishes. But in principle, when you hit it perfectly, if you focus your probe, there is from under to over focus, there is no contrast inversion. So you in principle always know where your atomic column is going. This is also a very early example from 2002 here, where people demonstrated just the distribution of doping atoms in a silicon wafer. And this is one of the early examples where people dealt with point defects. And this is just done by, in this particular case, like by ion implementation. This is a pretty heavy element, as before. To visualize the distribution of heavy elements is easier. Nowadays, people even deal with light elements or vacancies, like point defects, vacancies in such lattices. But this is just a very early example what you can do with atomic resolution stemming. This is another example that just shows the direct correlation between an HRT image with these, like, this is non-corrected in this particular case because we directly see these delocalization effects and the corresponding HR stem image, so high resolution stem image. There is even some contrast between this gold and the cerium oxide. If you look very carefully, the intensity of the atomic columns is slightly lower here, so the gold is heavier than the cerium. In this particular case, we don't see the oxygen columns here because, I mean, this is like, I would say with modern microscopes, it could be done even a little bit better, and using a bright field detector, one should be able to visualize the distribution of the oxygen columns as well. There's another example about the chemical contrast at the atomic scale. I'm going to go through that pretty quickly because these are, let's say, just examples. This is for shell particles, bimetallic particles with lead and gold, and there's a certain change, a certain difference in the atomic number. And this is what you clearly see between the inner core and the shell of those particles. You can see that everywhere there's an overview image, and you can do such an analysis. You can measure the intensity and determine the local composition by modeling, in principle, the intensity of the intensity variations on the atomic scale. So modern simulation tools, and I got through the internet yesterday to compile a certain list for you, which we are going to send on Thursday, about free software tools to do TM and STEM simulations. And in principle, it has become state of the art to do a chemical analysis on the basis of images. So you don't need an ES measurement anymore or a Niels measurement. People came up with the idea to use the local intensity because we know the scattering impact, so the atomic structure, the atomic form factor, so the scattering impact on our electron beam. We know in principle our beam current, this is what we can measure in the microscope. And people want to do quantitative analysis and derive local compositions by just determining the local intensity here and by comparing that to a distinct molecule. This is another very nice example. It's from 2007. This is the enrichment of just zinc oxide boundary here, grain boundary in zinc oxide. As you can see, there is a certain enrichment of dopant species. This is again a very heavy element of dopant species in the like periodic arrangement along this grain boundary. It's just upon further treatment. Let's look up to the bright field detector just to relate that with respect to light atom imaging. So this is a combination, yeah, these are two examples on the left hand side and on the right hand side. So this is strontium titanium oxide here on the left hand side. This is our unit cell, and in principle we know that we have oxygen, titanium and strontium. Let's have a closer look here. And in principle it's hardly visible that there are in principle these oxygen columns in between. So we hardly see these oxygen columns, we see the titanium and we see the strontium, but we don't see the oxygen. The same holds for this one. This example, this is titanium oxide. In principle we only see the titanium colors in the C contrast image, but not the lightweight element. The same is here on the right hand side. This is like a rare earth element and hydrogen, so very special case. And we hardly in the dark field image we don't see in principle the hydrogen. I mean the hydrogen is the lightest element that is available. But in the bright field image here, we nicely see the hydrogen atomic numbers. The same holds for the oxygen here and there. So you can clearly distinguish and measure distances of those different atomic columns. Here you see the hydrogen and the oxygen everywhere in between. And so by bright field imaging, because the scattering in forward direction is far more pronounced than the scattering in large angles for the light elements, this is what we can do with the bright field. Unfortunately, new microscopes, they allow just for the simultaneous recording of signals from different detectors, so you just insert all the detectors, you just acquire such a data set at once, and you can do all the data analysis afterwards. There's the last example about the spectroscopic capabilities. Yeah. I mean, common high-angle angular dark field detectors, this is what I forgot during the introduction. I mean, you can also use them as angular dark field detectors. And what you have to do is you just have to adapt your camera length. So you zoom in and out of your diffraction pattern. And let me just come back to this slide. Probably this is a good idea to talk about. So I mean, this is a very small camera length, So it's very low magnification of our diffraction pattern. If you enlarge the camera length, so you enlarge your diffraction pattern, some of those reflections can easily hit our HADAF detector, isn't it? So, and by doing that, we end up with some contrast that looks like this. If you don't want to have a pure chemical contrast, but you're interested in crystal defects, or you're interested in the grain structure like this here, then you do angular dark field, or you do bright field imaging. Because in bright field imaging, like you can see it here, you get some insight in all your defects of the material. You will see the grain boundaries because you probe the strain. I mean, there's far more behind that what I've presented you so far, because I mean you can even do some analysis of the distribution of local strain fields by such imaging techniques. And this is, I mean, there's a meaning behind in such a that you can do all, or many of these analyses that you come to with conventional TM mode. You can also see those contrast features in the STEM images. So you will see the lattice defects, you will see polycrystal material, you will get some insight in the grain orientation. If you just do a pure chemical contrast imaging of this structure here, you will hardly see, or probably not see, all those individual grains. Because I mean the chemistry here is the same. There is a zinc oxide. And I mean all those grains are zinc oxide. And if you get a pure zinc contrast image, you will not get any insight in your polycrystal morphology of the film. I mean this is the first question that we want to address. We want to see how like the layer grows. And finally we might be interested in some atomic resolution, whatever, or the local chemistry. But in principle, first question might be the morphology of your deposited film. This is what you see in angular dark field or angular or bright field. But you will hardly see that in zinc contrast imaging. I mean, this is what you want to have in zinc contrast imaging. You want to have all these contrast features because you want to derive, in best case, some quantitative numbers about your local density of your material flows. And you will see, I mean, many microscopes, they only have one angular detector available, which you make use of for both angular dark field and high-angle angular dark field imaging, but just adapting your camera length in your microscope. So meaning we're just zooming in and out the diffraction pattern, because it's cheaper. And the sensitivity of the header detector anyhow is pretty good. So it's dedicated for low intensities, because the further you go here, the lower will be the intensity. So the sensitivity of a pure HA detector is pretty high. Yeah?
Is there anything like annular bright field?
Annular bright field. Yeah, there is. I mean, you can use your annular dark field detector as an annular bright field. Just imagine that your annular dark field detector covers a certain angular range. And if you go up to very large camera length, so that your central disk just hits this active area and you zoom in further, then you might cut off your direct beam. I mean, there are such applications already published, but in principle, most microscopes, they don't provide a very dedicated detector.
But all anything has whether normal bright field or annular bright field, necessary condition is that the zero disk should go into that.
Yeah.
That is a necessary.
Yeah. I mean, the direct beam hits the detector. This is called a bright field. You might even use, if you only have one such an annular dark field detector available in the microscope, you can also record a bright field image. The only thing is, what you have to do is you have to shift your diffraction pattern onto the detector. I mean, this is not well defined because the zero or the lowest zone mount will also hit your detector somewhere, but you are always able to record a bright field image just for like an overview image. If you like the bright field image more than a dark field image, then I mean, this is not common, but in principle you might just shift that here. So for any reason, if you have special applications, you can just make use of the dark field detector like we can use this, like bright field detector. This is the same with our electron detector in SEM, which we can also use for backscatter detection imaging, fortunately. So let's come to the last slide, and then we're going to have a coffee break. So the last slide, this is one example about the combination of STEM imaging and our spectroscopic techniques, because I mean we have our X-ray detector available in the microscope. In many microscopes we might have a post-column or an inclined spectrometer for electron energy loss spectroscopy available, and as we address individual sites on our sample, I mean it makes quite some sense that we combine the analytical techniques with a STEM mode rather than with a conventional TM mode. I mean, if you're interested in a larger area, you might just eliminate that and measure your outcoming and your generated X-rays. This is what you can always do just for a rough measurement. But if you want to get, or if you want to like do some site-specific measurements, it's always easier to address that, let's say, with your in the STEM mode. Although I must say, if you do it with a parallel beam, you might end up with far higher current densities because you might go up to 2 nanoamps or so, which is for a regular field emission gun the maximum value, or for a very high current gun to 10 nanoamps. Then you might want to do that for very low concentrations, for instance with a parallel beam, or you might condense this parallel beam. Because here you are somehow limited, I would say, to 200, 300, 400, 500 picoamps. This is half a nanoamp, so this is like probably 1 order of magnitude lower beam current. And this is an example just of an heterostructure on strontium titanate. This is strontium ruthenate. These are 2 unit cells, 1 unit cell and another 2 unit cells. There's 1 layer of lanthanum inserted here. This belongs to this layer. So, and this is already an atomic resolution STEM image that was not recorded with a probe-corrected microscope. So this is an image of a non-aberration corrected microscope. And in principle, at 200 keV, a common and modern microscope should provide such a resolution. For comparison, this is the probe-corrected image, and you can see the resolution is in principle better by a factor of, like, let's say, 2 or 3 in this particular case. But what we see is that the contrast is far stronger than here, because the tail of the probe, is cut, and the local current density on the atomic columns is far better. This is why the contrast is better here than there. But in principle, this is what you should be able to come up. And I mean, we could think about to provide some or to apply some Fourier filtering, and even for publication, I would say this is quite reasonable. So this is what I did at Stanford. Without, they just have an image cell aberration corrected microscope, which is dedicated for environmental measurements. So they have a gas inlet. This was a probe corrected microscope in HP lab in Silicon Valley. So they have a double aberration corrected tool available. In principle, this is exactly the sample, just in a different site. And this is the combined EDS and INS measurement. So this was just raster scan 10,000 times or so, 1,000 and 10,000 times, to average the signal and to integrate all the spectra during recording this data set. It's not common just to leave your, let's say, electron probe on one atomic column for 1 second or for 1/10 of a second and then to go to the next in between. But what you instead do is just you scan the whole region of interest very quickly, and then you apply some drift correction. So you record another image from an adjacent site to compensate for drift, because if you don't do so, I mean, we are on the atomic scale. We want to come up with a decent, like, spectral intensities, isn't it? So the dwell time would be somehow, and if you only probe, like, let's say in this particular case, the sample might be 20 nanometers or 10 nanometers, you can imagine that for each atomic column there are only, let's say, 100 atoms or so. You just probe the emitted X-rays of a very small number of atoms, and within our dwell time, I mean those our measuring time, the sample might easily drift, let's say, by one atomic column or in one direction. This is why you have to compensate for drift. But if you do so, you require numerous frames or many frames to integrate the signals, and then you can come up with a like a 2D mapping of like the emitted X-rays to derive the elemental distributions. This is EDS, where you can directly see this is the ruthenium, the 2 layers of ruthenium oxide, strontium ruthenium oxide. This is 1 unit cell of strontium ruthenium oxide embedded, and there is 1 layer of lanthanum down here. So the lanthanum, we didn't get that in the EDS, but don't ask me why. Unfortunately, what you see here is what you hardly get is a clear distribution of the oxygen signal by EDS. Simply because the detector efficiency for the low energy X-rays is low, as we learned, and this is the signal, this is just noise, almost noise. You can imagine just looking at these distributions here, the local intensity for each measuring point is only a few 10 to a few, like I would say, a few 10 counts, element-specific counts that you can use of. So it's not like 1,000 counts per X-ray line that you may use. This is the complementary INS measurement. So this is the similar distribution. This is measured at a slightly smaller, a slightly larger step size, because here the exposure time was even longer than there. But in principle, you can do those measurements, I would say, with a really good sample. I mean, it's all about having good samples for atomic resolution, spectroscopy, and imaging. I would say on a daily basis. The microscopes are robust. There is hardly any drift, and if the sample is, let's say, if the sample is of high quality, and you can align that well. I mean, this is another prerequisite, that you have to align the sample perfectly in the zone axis, then this can be done probably within 1 day. So the data acquisition, this is not that much a big deal anymore nowadays. Now we have to spend far more, as we have done over the last tens of years in the data evaluation. So first of all, we have to design your experiment well. You have to really think about what you want to do. The data acquisition, this is not that much a big deal anymore. It's probably more about the sample preparation. This is the example that I showed you about this ion billing, where we face these issues with the damaging of these strontium ruthenium layers, and it's more about having really clean and perfect TM samples. So this is more like what we have to do. So with this, this was the last sample for the scan microscopy. And if you no further questions, we will have a coffee break. And this is, for instance, just some 3D like visualization of electron tomography works. I mean, this looks pretty nice, isn't it? So we have some TM sample, and you see that it somehow tilts. I mean, this helps a lot. On the one hand side, it helps a lot for me to explain to you how electron tomography works, but on the other hand, it's quite attractive to present such images. And there are pretty many viewer tools available, and if you have a model which you can easily generate, you can do such rendering and three-dimensional whatever kind of fancy visualization of any like model in material science or any technique or And so this was, I just wanted to comment on that whenever you aim on such a like publication, you have to deal with the quality and the appearance of your data. This is so just the length of the scale bars, the font size has to be the same. It's just simple things, but this is what many people don't address, and then they just fail in convincing the editor to send the manuscript out for the review. But let's come to the electron tomography. This is one of our last topics. After electron tomography, there is only electron energy loss spectroscopy left, and some examples of advanced in situ microscopy. Okay, in principle, there are only 2 sessions left. There are only 2 days left. And now let's come to the electron tomography, because I mean, you know tomography probably from computed tomography with X-rays, I mean, for any kind of like medical applications. But why do people do tomography? There's a pretty funny example of 2 rhinos, and you can hardly see where one starts and the other one ends. It looks like a 2-headed rhino, isn't it? So this is what Benjamin found on the internet. And I mean, this is quite a little bit confusing, isn't it? It's a little bit weird. So, but the explanation is pretty simple, because it's definitely not the rhino with the 2 heads, because otherwise, digestion might be a little bit challenging. So let's see, how does it look from the side, from the front? So this was just the side view. This is how it looks from the side. I mean, it's quite obvious, isn't it, for this particular case. But in material science, there are many examples where, because we only see our sample in projection, where it's not really clear what's up and what's down in the sample. And so from in that respect, we need some 3D analysis. This is electron tomography. I mean, you know it from CT, and this is why I would like to start with computed tomography first. So this is what you might have seen already, probably some were already situated down here. So this is an X-ray tomograph. What you can see here, let me just restart the video. What you see here is the rotating part that makes quite some noise in the tool. And here you already see this, this is just the series of projections in different directions. This is just the skull of a human. And you see that in principle, there are different grayscale values, depending on the imaging mode. In the TM, you will see that it's far more complicated than in X-ray tomography. In this particular case, we have an X-ray source, and we have a line detector. And what happens in this particular case is that those X-rays, they just propagate on linear trajectories, and they become absorbed. And this attenuation coefficient depends on the local density of matter. Okay? In this particular case of this human being, just the skull, which is of bone, just shows pretty high attenuation coefficient, while the soft matter in the center just shows a lower attenuation coefficient. Okay? And just along these different trajectories, the intensity is measured. This is pretty simple. So we measure the final intensity, which is simply given by the integration of these different attenuation coefficients along our trajectory. Okay? So, but there are some challenges with, as I mentioned, with just this projection or this view in projection, because we don't really know. We just measure this intensity drop. We might know this initial current density or current. So we cannot distinguish between such a sample and this one with, let's say, just intermediate or average attenuation coefficient. So it could be different samples positioned in between that just cause the same final measured intensity on the detector. Okay. I mean, this is quite, the same holds for mass thickness contrast in TM, or in STEM imaging. It could be either a thick sample that causes some contrast in dark field STEM imaging, or it could be just some heavier sample. We don't know. I mean, it could be a thin heavy sample or thick lightweight material. So we cannot distinguish just by looking in along one projection. Okay, this is why we need some tomographic techniques. I hope that this is, I mean, the fundamental to understand why we need these 3D techniques and what is in principle done to reconstruct this physical parameter. In principle, we don't reconstruct the density here in CT. What we reconstruct is the distribution of this attenuation coefficient. The attenuation coefficient, that is related to the density of the matter, okay? But this is what we obtain by reconstructing the data. And the way is the following. We record projections of this intensity distribution along different angles through our object. And we end up with all those projections. Like later on, we will see many tilt series along different tilt axes. And we know that we can, I mean, this is just the logarithm of our incoming current and the measured current along this line. And you can directly see this is the projection. And you will see that this is just called the so-called radon transform of our attenuation coefficient. And now we know that there is a certain relation between the measured intensities here and our attenuation coefficient, and we have a certain transformation which just transforms this or projects along these lines into this distribution here. This is the radon transformation. We are not going into the details, don't worry. But what we know from this here, that if we calculate the inverse radon transformation, that we can directly calculate our mass attenuation coefficient in three-dimensional space by this inverse radon transformation from the series of our projections. Okay? So this is what this is called a back projection. This is done by calculating this inverse radon transformation. In principle, this is one way how to reconstruct the data. We will later on see some more modern techniques how to reconstruct, because there are several issues just with a simple approach. Because the necessity here is, or the like prerequisite is, that we in principle have an infinite number of projections in different orientations. But we never have an infinite number of projections. So we always have a discrete number of projections. And this already causes some trouble. This is already pretty old, so from the early 20th century. And yeah, this is pretty, popular. Just let me show you one example about which scales we can reach by electron and computing tomography with X-rays. So this is, I would say, one of the largest CT instruments. It's at the Fraunhofer Institute in Fürth, which is close to Erlangen, Nuremberg, Germany. There we have an X-ray source and a lie detector. It's a huge hall. And they have a big table to rotate almost everything. They put like a Porsche sports car on that, or a complete container with equipment for 3D analysis. This is not only 2D. I mean, for 2D, we have those at every harbor just to screen containers and trucks, But this is done in 3 dimensions. So this is like, pretty huge objects can be investigated. But let's have a look where electron tomography is. Because I mean, most of you might be familiar with computed tomography. Okay, so this is like what people use also in material science to gain some insight into materials on, like with a certain resolution, let's say down to the micrometer scale. Probably, I mean, the micrometer scale, this is, I would still call it micro-CT. So the resolution, the voxel, like the resolution, this is not the voxel size, but the resolution. These are objects that you can distinguish in 3 dimensions. In micro-CT is of the order of 1 micrometer. And the sample volume for such micro-CT might be of the order of millimeters to centimeters to the probably half a meter or so, depending on the resolution. So for smaller samples, the resolution might be a little bit higher. Nowadays, there is a so-called nano-CT available with a totally different imaging system. And in the former years, people realized nano-CT at synchrotrons with a very bright source. Nowadays, there are even commercial tools available for the lab that allow for a certain resolution, let's say, of down to 25 nanometers by using X-rays. I mean, 25 nanometers object size, this is still not, I mean, for material science, for some of the people who work on nanoparticulate materials or nanomaterials, 25 nanometers, it's somehow limiting, isn't it? On the other hand, the sample size for such tools is of the order of, let's say, 10 micrometers to 50 micrometers or so. This is the object size. Now we have the focused ion beam available, and we already saw some of these sectioning tomographs in the fifth session, where we end up with a 3D, let's say, resolution of down to 1 nanometer. And I would like to show you that with scanning as well as transmission electron microscopy, we are nowadays able to go down to the atomic scale, so you can do 3D analysis on the atomic scale. But you can also go up to sample volumes, let's say, or sample thicknesses even of a few micrometers. So you can start coming from like a few micrometers cubed down to only very few nanometers if you think about nanoparticles. There is another tomographic technique available down here, which is called atom probe tomography. This is a destructive technique where you just remove all the atoms from a fine tip on the surface. By using a mass spectrometer, in principle, you just determine the nature of all these species, and you do that some sequence, and to remove the whole tip and finally calculate the positions of all those different species in the material. Scanning and transmission electron microscopy tomography is non-destructive after preparing our TM sample, but the TM sample remains. Fit tomography, on the other hand, just removes material, so this is not destructive. Okay, by that, I mean you can cover all the different length scales by tomographic techniques. We can do 3D analysis on all those different length scales, meaning that there are even like correlated microscopic projects where we start at high magnification, if you just think about track propagation in an alloy or so, and then finally you go down, I mean, probably to the atom probe. This is only one example that you already saw about fit tomography, where the sample is removed slice by slice, and in each slice we just determine either the local microstructure by imaging or the local chemistry by energy dispersive spectroscopy. And I mean, this is, you can combine all that. You already saw that, so I'm not going into the details anymore. Let me just show you this example again, because here, I mean, you see very nice channeling contrast, so the sample quality during this fit milling is always pretty good for such channeling contrast, to observe such channeling contrast of the different grains here and the twins within those grains. So you end up with quite high contrast. You don't have to deal that much with the sample quality because you're anyhow going to remove material using the gallium arc. Okay? Then finally, I mean, they came up with a 3D distribution of the elements. I mean, here we are on the order, like let's say, of a few 10 micrometers. So So the lateral resolution of this mapping might be like there might be 2,000 pixels, like it's of the order of a few nanometers. Okay. So this is how TM or STEM electron tomography works. In principle, we have two steps. First, we record images along, like projections along different directions through our TM sample. So we need the tilt series first, and we have to align that tilt series, so we have to spend a lot of effort in aligning the microscope because we have to tilt very precisely, so the sample shouldn't shift very far because we want to keep it in our field of view. There are many automated alignment routines that even follow our sample, so there is some drift correction for each tilt angle. But in principle, this is what we derive. It's a tilt series of images. In this particular case, this is gold particles on the carbon support film. In this particular case, I applied dark field STEM image to record because it shows a very nice contrast. As you will see later on, there are some, some challenges depending on your imaging condition that you apply. In this particular case, those are polycrystal tilt particles, and you can easily imagine that whenever you tilt a particle which is crystalline, then in conventional TM imaging mode, you might end up with some diffractive intensities and intensity fluctuations. There is a certain requirement to do such reconstruction in the second step. So the second step, or let's say the second step here is the alignment of the tilt series. And the third step, this is the reconstruction. So use various techniques to project this intensity distribution back into real space to come up with a three-dimensional distribution of our physical property. I mean, the physical property here might be the local density, but in principle it's based on the interaction. And the interaction that we have here, this is in principle the scattering. So this is the scattering effect, our scattering, like our atomic scattering interaction with the material. And we definitely, or best case, in principle, for reasonable reconstruction, we need a monotone function. So meaning that either the thicker the sample is, the higher is the intensity that you measure, or the heavier the material is, the higher is the intensity. If you end up with this weird Bragg diffraction, and you might get in and out of zone axis, your intensity will fluctuate, and there is no reason for that except Bragg diffraction. But it has nothing to do with like the local thickness or the local density of the material. And this is why these conventional TM imaging modes are like rarely applied to conduct such electron tomography. So let's come to the data acquisition. First of all, I would like to show you a few examples of electron tomography, so that we have any idea what you can use it. This is an example of photonic crystal structures in butterfly wing scale. So people are interested in photonics nowadays. They want to generate artificial photonic crystals. And this was a project where we investigated individual crystal lights on the micrometer and a meter scale, how the chitin is distributed within those wings. These are scales of butterfly wings. We prepared them for TM. And this is just the final distribution of the chitin that causes this green color in this particular case. The second example is from Berkeley National Lab. And these are dislocations in some particles, lead particles or precipitates in aluminum. You see a really dense dislocation microstructure or dislocation distribution. And just, this is the three-dimensional distribution of this dislocation network within our sample. So you cannot only apply that to defect-free materials. These are two examples. These are two examples of like nanoparticulate or nanostructured and highly porous materials. This is a particle that you already saw in one of our lectures. And this is a strontium titanium oxide film, an open porous film on a silicon substrate. This is a tin series. In this particular case, both are used for catalytic applications, and people are interested in the pore size, and pore distribution, and pore conductivity. We which you cannot get just from a single projection. This is a standard image here, for instance, where you see a chemical contrast here between the silicon, the titanium oxide, and another platinum coating. There's another, you already saw this example. This is another very special tomographic technique about this bilayer or trilayer graphene and the crystalline membranes. And this is the distribution of particles. These are aluminum oxide particles distributed in an epoxy. This is used for electrical applications, like for transformers, for instance, as insulating coating. Okay? So there are many questions, like people might be interested in the 3D distribution of any like material and density variation, like the porosity or the defects. In the transmission electron microscope, we have two ways how to record a tilt series. I mean, the simpler way, and there are many holders available, is such a very thin regular holder that just clamps our TM sample. But with this, you can easily imagine that we are somehow limited with our tilt angle range, because we cannot tilt to 90 degrees, because with such a sample, the sample would just shadow itself. Okay? Meaning that we have a certain missing wedge, so-called missing wedge, and this missing wedge causes artifacts, because in that angular range, we don't detect any information about our sample. So during the reconstruction, we cannot say anything about the sample in this particular direction. And this direction is shown here. So this is the particle in principle lying on a TM support film. If you tilt that from the top, you get very clear and sharp boundaries of our pore structure here, for instance. But from the side view, or from the side, we don't get any information. So we don't really know where the particle ends, because you don't see it in that direction. Okay? This is why during the reconstruction, those so-called missing wedge artifacts form. So we end up with an elongated structure in this direction, because of this missing wedge. Another way to record tilt series is to prepare a pillar of our material, or to deposit nanoparticles at the very end tip of such a so-called sample holder here. And there are sample holders available that allow for the rotation of the TM sample by, let's say, 100 or 360 degrees. This is why it's called so-called 360 degree electron tomography. You can imagine, by doing tomography or by recording a tilt series using this holder, we can cover the whole tilt angle range. Okay? So this causes somehow artifacts. There are ways, reconstruction techniques to minimize those artifacts. Here we directly cover the whole tilt angle range. This is how such a sample holder looks like. It's just an enlarged view. So we just have two clamps, and it's thinned down here and there to allow for pretty large tilt angles already. So we can probably go up to 75 degrees out of 90 in both directions. So there are probably 15 degrees missing. What you can see, there's just one criterion shown. In principle, the number of projections here, the number of projections limits our final resolution in the tomogram. So the more projections we record, the better is the resolution. I mean, this is a general finding for electron tomography. And there is another aspect, this is this elongation factor due to this missing wedge. And in principle, it says the larger this missing wedge is, the larger is this elongation of our structures, because we don't collect information in that direction. So just let's go a little bit more. Let's discuss a little bit in more detail how these missing wedge artifacts form. So this is just our test object. This is a well-known test object, which is also used for X-ray tomography. Just assume that we only have projection in one direction. Now we do the reconstruction. How does the reconstruction or volume looks like? And we only use one projection. We project it back, and this is the intensity distribution, or this distribution in 2D, or now in 2D, that we will see. If we use a second one, like a second projection, or some more, this is 20 degrees already, we can already imagine that there is our object. And if we add many more projections, we get closer and this reconstruction reassembles our somehow our object. And this is for 180 degrees. You see that there are still some artifacts due to the discrete number of projections, but still it's very similar to our object. And now if you remove some, so let's see, we are able to tilt up to 70 degrees, then we end up with this, let's say, elongation of the structures, and it's smearing out of information. Okay? I mean, during the rendering, because you come like evaluate and do some post-processing to your data, you will commonly cut that to a certain extent, but in principle, if you want to measure some extension of the particles or the size in this particular direction, I mean, you will end up with a systematic error which is quite large. Okay? There are a few ways how to minimize this missing wedge artifact. This is just here, we have this missing wedge because in this particular case, many people can't only recorded tilt series along one tilt axis. You might think about to rotate your sample by 90 degrees or to record a second tilt series. This is so-called dual axis electron tomography. By that, you only end up with a very small cone or like a small missing pyramid of information. Okay? I mean, this is quite common with a regular electron tomography holder. You might even reduce that further, but in principle, this is already pretty good compared to the single axis tomography. But now let's come to this 360 degree tomography holder. I mean, because I would say it's not necessarily easier, but the data quality for quantitative analysis is quite better. So the sample holder looks like this. You have a fine tip which you might also use for atom probe tomography, so you can do correlated microscopic analysis. You can just use such a tip to prepare an APT sample, to study it in the transmission electron microscope first, and then to transfer it to an APT to do like the atom probe measurement. With a very fine tip, which is directly positioned on the rotational axis of this strip here, and this is how it looks like in a scanning electron microscope. And I mean, this is still pretty coarse, isn't it? So you position any structure on top, and you might want to shape that using the focus 9 view by just removing some of the material. But in principle, this is what is mounted with this tomography holder. And I mean, it's not that the tomography holder rotates by 360 degrees to rotate all those projections. It's more that you can use the stage of your microscope to cover a tilt angle range, let's say of plus minus 70 degrees or 60 or 50 degrees. In this particular case, you rotate the holder by 60 degrees or by 120 degrees. And then you use your stage again to record the second set of projections, and you rotate it from 120 to 240 degrees, and by that you cover the whole tilt angle range. And then you have three data sets that you have to combine and that you have to align, and this is what you use for your tomography reconstruction. Yeah. Exactly.
And they are calling the very high, the detector size is very high. So the solid is very high. So in that case, we will end up with this missing parameters.
Yeah, you also have this missing wedge, because there's, I mean, with this detector you cannot tilt up to 90 degrees. You can only go up to 70. So this is why you always have this missing wedge, so you don't, gain any like inside in the structure of your material. The 360 in principle is ideal for electron tomography because you directly record a full data set of projections. You will see that there are some examples about where you will see these missing wedge artifacts in the 360 degree tomograms. In principle, you don't have this, let's say you don't have this missing wedge artifact, but what you do have is, I mean, you have to combine these three sets of projections. And this already causes some trouble because if the magnification slightly changes, because you do it mechanically, so you have to realign the height of your sample in the microscope, you have to reposition that, and by that you might introduce a very, like a minor change of your magnification, but that shouldn't be more than like, let's say, it's like a 10th of a percent or so, because in worst case, if the projections are simply larger than the first series, you would have to correct for that. And I mean, there are software routines available and software packages available which actually do that for you. Just there is some iterative procedures which even allow for the optimization of the tilt series during the whole reconstruction process. Because what you currently do is you have all your projections, you back project or you reconstruct your structure, and from there easily calculate new projections that you can compare to your experimental data. And then you adapt certain parameters for the alignment for the reconstruction, and in the second step you do some iterative reconstruction. So it's a little bit more complicated than just back projecting all the information in real space. There are various approaches how to optimize that. So there's one example that I already showed. It's this open porous titanium oxide. There's a thin film on the surface, and those pores are connected. This particular sample was prepared by a templating of tiny spheres, and then there was some soil gel coating, probably, to generate these open porous titanium oxide films. The question was about like gas transport for catalytic reactions, so there's like some interest in this property, and it was about the optimization of the pore structures for the application. And so these are the two examples again of like this regular conventional electron tomography and the 360-degree tomography. And I mean, to come up with such a 360-degree tomogram, you would need to prepare a certain pillar, you know, and you would have to transfer that onto your sample folder or your sample mount. This might be pretty easy. In this particular case, you could simply prepare from such a sample. This is based on a silicon wafer. You could just prepare a plan view sample by just, you know, cutting one piece of the sample, backfilling the sample by dimpling, for instance, or an argon ion beam. And then as you reach certain electron transparency, then you can just use the sample in your sample holder and just tilt it up to 75 degrees. So the conventional electron tomography sample preparation is far easier. You don't need a focused ion beam, and you can do some reasonable work. I mean, this is not, it's not that you necessarily need the 360-degree tomography. But it is, I mean, there are larger pores and there are very, very small pores embedded within the titanium oxide, which are not active during this like the catalytic reaction. But in principle, the resolution here in EEG is better. This is like for sure. This is how we prepare the sample using the focused ion beam. We just extracted such a pillar, we mounted it onto this metal tip. Here it's filmed using the focused ion beam until we reach a certain thickness or diameter of the pillar, you know, which is still sufficient on the one hand side to cover like a pretty decent volume of our material. But we want to end up still with an electron transparent sample. You know. This was the final size, so there's a platinum capping, so this was just a protective layer on the surface of the material. There's carbon deposited, simply due to like the contrast to the titanium oxide. This is our titanium oxide layer, which is of the order of 100 or 150 nanometers, and this is the silicon wafer. Okay? And this is what you now use, and you just rotate your sample to measure projections. This is already a projection in STEM mode in the microscope, and this is just the observation of one specific angle. And now if you just rotate your sample by 360 degrees, then you see just this overlapping intensity variations due to the like the pore distribution here. There are no videos in the printout. Unfortunately, there are many in the presentation here. But nonetheless, in this particular case, we make use of the fact that we know the crystal orientation of the substrate. We clearly see this very thin layer of silicon oxide on the surface. So we could even align that almost perfectly parallel to the electron beam in STEM mode. And this is the data set that we use for the reconstruction of the 3D distribution of the pores within the titanium oxide. Okay? This is just after reconstruction, so this is just a fly through the structure from the substrate, or this was from the carbon, from the ester-positive carbon, through the material, and we finally end up in the silicon waveform. And I mean, you see that there are still some intensity variations. This is the reconstructed, so you can see there are intensity variations. The reason for that might be that the titanium oxide is crystalline. You already saw that here in this tilt series, that there are some intensity, let's say, fluctuations. Do you see that? So sometimes it's just brighter and darker, meaning that in principle, this monotone, this requirement is not fulfilled here. So we don't have this perfectly monotone function, or the intensity doesn't necessarily, it doesn't exclusively depend on the local density of the material. So this is the EF. There are, to some extent, just limitations, because in HAEDF, the measuring time for one image, for one projection, might strongly exceed the measuring time in ADF, so the sigma might be pretty low, and you might introduce damage of the material, or damaging of the material, and so you are somehow limited in that respect. But nonetheless, I mean, here are features which are separated, like pores which are separated with a resolution of around 1 nanometer cubed, and this is like the resolution that you are able to achieve for such measurements. And based on that, on such measurements, we modeled, or some colleagues modeled, like in this particular case, this is the first, this is just a so-called sphere inscription technique, where you measure the pore size and the connectivity of the pores. You might compare that directly to some absorption experiments. And I mean, you always have to ensure that this is somehow reproducible, so that the material is homogeneous on a larger scale. If you want to compare that to like gas absorption experiments, for sure. But in principle, what people came up with in this particular case was diffusion, let's say diffusion coefficients through those layers based on our measured distribution of pores and the interconnectivity of the pores. So maybe for catalysis, this is like one major question, how pores are distributed. And this was just one example about scanning TM imaging as a mode to record those projections. In principle, depending on your material, you might use every imaging technique that is available in your microscope. It has in principle only to fulfill like your projection requirement. This would be the best, like even for the titanium oxide, this was an earlier example. In principle, you would go for a pure C-contrast imaging mode. In that particular case, for instance, to distinguish between pores, just your titanium oxide to end up with the highest contrast in the reconstruction, or the clearest, most reliable contrast, let's say, in the reconstruction. But as well, you can use spectroscopic techniques to record projections. I mean, people did already EES as well as EES tomography. You just have to keep in mind somehow, because I mean, if you record, just let's imagine that you record an X-ray mapping along one projection. If you tilt to very large angles, you will end up with some shadowing. And you would have to deal with all the absorption for very large tilt angles. The path of your electron beam through the sample gets longer and longer. For 70 degrees, this is already pretty long. You just have to think about how to quantify your data, because I mean, you want to use probably quantified data, not just the signal distribution, but quantified data along the different directions to go for a reconstruction of the elemental distribution of the material. But even in hills and energy filter TM, you can use almost any signal that roughly fulfills, or that in principle fulfills your projection requirement. And this is the problem about conventional TM right field imaging. I mean, you already saw that in scan imaging as well, but in scan imaging it's a little bit easier to overcome that problem by going for high angle in the dark field. In conventional TM, you always have this strong gray contrast. This is all gold islands on the surfaces, And in principle, each of these islands appears at a different intensity. And I mean, this is what is hardly, or what is a little bit challenging to use it for the 3D reconstruction. There's one example of crystalline particles embedded in such an epoxy. This is an example of an amorphous material. So for the amorphous material, we just have this mass thickness contrast. This is a perfect data set for electron tomography. You can also use that one because, in principle, there is a strong contrast in between those particles and the polymer if they are not aligned in any gram condition. So there is some mass thickness contrast. But you would not be able to distinguish between the local density of different particles of different sizes. This would be pretty challenging. So just assume that you have two species of particles here, you would probably not be able to distinguish. And for Siemens company, it was of interest how those particles are distributed depending on the density of the particles, whether they agglomerate or not. And so we did some analysis on that just by measuring, let's say, the distances between those particles to come up with a three-dimensional distribution in real space, because like this is just, as I mentioned, insulating coating for transformers, and the question was how to enhance the lifetime of the polymer. So this was just in this particular case. There's another example of polycrystalline. This is highly open porous, nanoporous gold, which shows like exceptional mechanical properties. So some of you might know about like the smaller is stronger. So there are limitations for like, the generation of defects, the movement of defects, the interaction of dislocations. And this is why people are interested in like open porous gold, but to understand the properties, you would have to correlate that to the local distribution of the material. This is why one of our students did electron tomography on the distribution of these struts. This is just another example, and here, this is already high in a dark field, and in principle what you see here is that there's hardly any contrast fluctuation. I mean, this is single crystalline, you see some broad contrast variations in the back, but in principle you get a really good contrast of the gold, which is bright, compared to the vacuum, which appears dark in this C-contrast range. This is another example. As you see, I'm just going to show you some examples right now about a very complex structure. This is for the absorption of infrared light, where you have for like detector applications. And in principle, there are lead selenide particles which are grown on carbon nanotubes, which are used to separate charges here due to the incoming infrared light, because the material is highly sensitive in electron broadcast form, and you want to separate those to detect infrared light. And this is how the structures look like in C. This is a regular dark field again. You see the nanotubes just at a lower intensity, some holes. This is just such a nanotube network. You see all these lead selenide particles. And the question was about, you can easily imagine that it strongly depends on the interaction of those particles which are grown on this network here and the carbon nanotubes. Because the interface gives you some insight in like this charge separation and the efficiency to measure infrared light. And it also depends on the size and the shape of those particles. This is the reason why we applied Benjamin applied electron tomography, and this is only one exemplary particle. I mean, you can simply imagine that those particles grow around the nanotube somehow, and this is what you already see here. So this is the nanotube strut, and this is the lead selenide. There are again some fluctuations because we are in like ADF mode. The tilt angle range here was between plus and minus 70 degrees. So we have to expect a certain missing wedge artifact. But in principle, this is like a reconstruction with some contamination around after the reconstruction already, how the shape or the morphology of such a particle looks like. But moreover, what you can do is, just for exactly the same particle, you can do atomic resolution imaging to gain insight like in the crystal structure, whether it's like polycrystalline or semi-crystalline, those particles. And you can gain some insight in the interface between the nanotubes in this interior. This is just shown for different orientations, as it is shown here, because we know the shape. We know how to interpret the atomic resolution contrast, because otherwise there would hardly be any chance. I mean, you just see the projection. In some areas, it shows some nice, contrast. In some areas, the atomic resolution contrast is pretty poor. This is due to the local, let's say, defocus and the local sample thickness. As you know, the thickness and defocus strongly, govern your contrast mechanism here. This is how you can interpret for complicated 3D structures your high resolution pictures. Now let's come to nanoparticulate materials. So people are interested like in the shape of nanoparticles or the morphology of nanoparticles and the properties. I would like to show you two examples of porous particles. But there is always a question how to prepare samples. I mean, for bulk samples or for thin films, you already saw this film tomography, or you can just back thin by applying mechanical or grinding and dimpling. But for nanoparticles, it's a little bit more challenging. We have this tip, let's say, for 360-degree tomography. I mean, for conventional tomography, you might just simply disperse the nanoparticles onto a TM support film. This is how you come and do that. And you hope that those particles don't move while you record the still series. Why would they move? I mean, they wouldn't move due to gravity, so they stick to the support film, and as you tilt to large angles, they wouldn't drift, so this is not a big deal. But what happens is that the support film might shrink, so every like a lazy film or really carbon film that was prepared from a polymer due to like any kind of a pyrolysis step, the film might shrink and move, so it's not the particle itself. That might cause some trouble because even the tilt angle, the relative tilt angle might change. Right? So this is a movement, just a movement in the plane. This is not a big deal because this can be easily compensated for, but it's just a change of your support. For 360-degree tomography, you might deposit it somewhere onto your tip. The simplest way is just to dip code, or somehow to code your tip, but it's hardly improbable that your particle will sit at the uppermost tip of this pillar here. This is where you want to have it, because otherwise you might see some of the particles sitting around here. If you tilt that, you will end up with a strong contrast. In this particular case, this is iron oxide. This is a metal pillar, copper pillar. And if you rotate that, you will end up with a shadowing, a strong contrast contribution of your pillar in this particular case. So this is why we developed a technique. These are the particles I'm going to talk about. These are these zeolite particles on the one hand side, on the other hand, these iron oxide particles that show some porosity for electrolytic applications probably. This is why we developed a technique to transfer individual particles onto pillars. You already saw that during the fifth session, and I'm going to skip that. I'm going to go through that very quickly. What we in principle did is we just reshaped this metal tip using the focused ion beam to come up with a final tip with a plateau with a certain diameter of the order of the size of our particle that we're interested in. Meaning for small particles we use a small plateau, for larger particles we use larger plateau. This can easily be done. And we even cut the plateau by just tilting this pillar in the focused ion beam, and then we have almost perfectly flat plateau. This is how we approach such a particle from the bottom. I mean, this is the particle just dispersed for any kind of TM analysis or SEM analysis onto a TM support film. This is our grid here, our copper grid. This is this support film. There are some of these particles. This one is situated on the bottom of our support film. We look from the top. And this is already our pillar that approaches from underneath using our stage. So the pillar is just mounted to the stage of our microscope. The grid is just clamped in a nano, like such a nano manipulator, where you can use almost any kind of you just need a steady position, and you have to move it in X and Y because you want to have it somewhere under your electron beam to identify one of those particles. And then you can just use the stage to approach a sample and pick it, or your particle, and just pick it up from the support. And this works quite well. So this is an individual particle, and you can even do the same experiment using like a well-defined and chosen particle. So you can select an individual particle for the transfer procedure. Here we use some epoxy, so there is a little bit of blue in between, which we don't see in STEM imaging here. This is AEF. You see this strong contrast variations. This is almost high angle angular dark field imaging, so this is the better way in principle. This is what we use for the reconstruction of those samples. And this is how the distribution of material within those particles looks like. So in this particular case, we have a high degree of interconnectivity, while for this other sample here, for these tiny particles, those pores are embedded in this iron oxide. This was one particular application. This is a fidelity application. And based on that, we might again come up with some like distribution of pores, pore sizes, interconnectivity, and all that, in which the catalysis people are interested in. And I mean, you have to keep in mind that this was only a single measurement of an individual particle. If you want to gain some insight, like if you have a very heterogeneous distribution of properties of particles, I mean, this is very homogeneous material, and then you have to think about how many structures or how many samples or particles you would have to measure. This is the comparison of scanning TM imaging and TM imaging for very big samples. So this is a sample which is, in this particular case, it's a biological sample of cells. This is almost 1 micrometer. And this is the tilt angle here. And 1 micrometer sample, like almost independent of the accelerating voltage, like 1 micrometer is very big. This is how the sample looks like in STEM mode. This is how it looks like in STEM mode at very high tilt angle. So you can still work with that, but you will hardly see anything in TM mode. So this is why for thick samples, in particular at lower densities, you prefer STEM imaging. And I mean, I don't have to go into the details why the final reconstruction looks far better than for the STEM, via STEM data. So this is the big advantage of STEM. Imaging in principle provides higher contrast and finally better resolution for thick samples. On the other hand, for biological or organic materials like polymers, you might end up with beam damage because you have a very fine electron probe, so the current density is pretty high, and you have to assure that your sample doesn't move during the data acquisition because you have a serial acquisition of each individual projection. And if the sample drifts or your scan field drifts due to any reason, then of course you might end up with artifacts in the reconstruction. So for the thick samples, let me show you one example, which are these butterfly wing scales. So this is how a butterfly looks like. So it looks somehow like a fish on the surface. The color of this Calophyllus crudi, so this very special butterfly, it's not given by any pigments, but it's caused by the distribution of chitin within all these wing scales. So the size of these wing scales is pretty small. So you can see here, so it's 40 micrometer by let's say 200 micrometers. And this is how an individual wing scale looks under the light microscope. You see that some of these individual areas here, they appear green, others don't show any color. The reason for that is that there are as well those crystallites, but they are misaligned with respect to the incoming light. So the reflectivity here is given by the optical properties and by the distribution of chitin, which shows like a different dielectric constant compared to air. And this is simply what happens. Then I'm going to skip the details about plasmonics here. I think some of you might be familiar, others might want to figure that out. But in principle, as I mentioned, it's the distribution of chitin. The question in this particular case is the light is not only green, but it's polarized in a circular way. And the question here was whether those crystallites, they are right-handed or left-handed, because there is a certain asymmetry for different crystallites. And so the question in the first case was to determine like the crystal structure of those photonic crystals, so the distribution in general. And the second question was whether or not those crystallites all have the same chirality, called handiness, or different chiralities. And this is how those samples were prepared. So I mean, you can imagine those are just 40 by 200 micrometers. This is pretty small. I mean, even for TM sample, these scales are very small. And our technician, she just used a single hair and the adhesion to transfer these onto, this is just another grid support, a TM support. And as you can see, we didn't apply 360-degree tomography then, so this was impossible. But you will see that we had to do some TM sample preparation using the focused ion beam. Because you can easily imagine that if you tilt the sample, and those are already 3 micrometers, although they exhibit a certain porosity, 3 micrometers is very thick. And in worst case, the electron beam would have to propagate through 3 micrometers of chitin. And you can easily imagine that if you tilt up to, let's say, 70 degrees, the path would even be longer by a factor of probably 2.5 or so. That would be like 5, 6, 7 micrometers. Okay? And this is an extremely thick sample. So, but nonetheless, so we came up with a preparation. This is how such looks like in the transmission electron microscope. So this is already in the ring scale without any further preparation. You see those crystalline areas where we have this nice periodic distribution of the chitin. Everywhere where the image is dark, this is dark field stem imaging. There is just vacuum in this particular case. And here you see some struts that just support, it's just for like the stability of those rings. So the sample is thicker here at all those lines. And here you see such a polycrystalline microstructure of the ring scale. So, and this is how, in principle, this is the expected distribution of the chitin for these chiral, photonic crystals. And this is just 1/2 space is filled with chitin, the other one is just filled with air, which gives us the properties. Now we have to think about for this very thin, very, very thick sample, we have to think about our depth of field. Because now the sample is already 3 micrometers and current TM investigations are not done at 3 micrometer sample thickness. And if you do that study using a regular stem probe for stem imaging, what you will see is that on the top and on the bottom, some of these are marker particles, gold marker particles for the realignment of our tilt series. They already get blurred, so we lose resolution because our probe broadens in a certain, and we just assume that your sample has a certain thickness. It's like in a scanning electron microscope, if you have particles on top and on bottom, or object features on top and on bottom, that they would become blurred, or the projection would be blurred. And only a very small, region of our sample would be in focus. This is why we even lowered the convergence angle, and modern microscopes allow for that. So this is an example of 10 milliradian. This is like a common probe for scanning TM imaging, even like probably atomic resolution imaging. This is only 1 milliradian. So this is more microprobe mode. So we'll let you know it's microprobe. Where we see all those particles, the size of these particles here is 30 nanometers, and the resolution under those conditions is far sufficient to do such a tomographic analysis. So for thick samples in STEM mode, you have to think about the convergence angle. Even you can tailor that, so you can adjust that. The second aspect is that, in principle, this is what I already mentioned. For very thick samples, the samples would get even thicker if you tilt them. And this is why we cut these ring scales using the focused ion beam to realize samples that look like this. Because if you tilt those, you might even limit the projected sample thickness. You might be able to do some better work. But you can easily imagine this is chitin. This is an organic molecule, the distribution, there's nothing else in it. And you can easily imagine that wherever the ion beam hits the sample, it gets immediately destroyed. Okay? Totally destroyed. And this is how our technician removed the material without exposing the central area to the gallium ion beam at all. So you can do that blind, just by watching 1 or 2 times using the electron beam, then just adapting these scan fields for the ion beam. This is what Christina just did in a blind way. So she removed almost all that material. And finally, we came up with such samples with a width of 1 micrometer or 1.5, and a thickness of like 2, 2.5 or 3 micrometers. And if you now tilt that, you don't up with severe shadowing. Okay? Unfortunately, this is another just side comment. What happened, due to this gluing, we introduced some tensile stress. And by removing that here, this is what we didn't expect in the beginning, we ended up with some elongation and some deformation of the material just by removing the upper and this lower part. But this is just a side comment, but nonetheless, we were able to reconstruct the 3-dimensional distribution. But this is something that you have to keep in mind if you prepare samples. This is how a tilt series looks like. So, in some projections, we already look along some of the, let's call it zone axis, like these highly symmetrical directions of our Titan structure. And then samples shown that have this left and right-handed gyroid structure. I mean, you don't see that from the projection because this handiness, you know, this the projection, it could be both. So only by reconstructing the 3-dimensional distribution of the Titan, we are able to distinguish between these 2 different ones. And these are just 2 reconstructed volumes, and you can nicely see that this here, in this direction, you know, it's just a right-handed structure, the other one is a left-handed structure, and it turned out that in this butterfly there are preferential like 80 or 90% only these left-handed structures, not the other ones. I mean, this is what you can also directly relate to optical properties. If you do a measurement using microscope in reflection mode, with and you have a very fine light optical beam, then you can do those experiments and you can attribute, let's say, the polarization of the light from an individual photonic crystal. And you can do a little bit more. The scanning theory is pretty easy. You can even derive some texture mapping, for instance. People who work on metals, they can easily understand what that is here. Just by looking at those crystal lights, you see that some are already aligned very nicely in some highly symmetrical aligned with respect to the surface of the swing scale. And this is what gives us this bright color in a certain angular range of such a butterfly or an insect. Then we come just to some of the challenges. On the one hand side, we might end up with some limited tilt angle range in regular tomography. This is what you already saw. We could either apply some elaborated reconstruction algorithms to minimize missing match artifacts in their ways. So nowadays we don't use this simple back projection, like a wave back projection, which they make use of in CT. This is the minimum, but there are even far more elaborated techniques, like compressed sensing techniques and others. Or you might come up with a 360-degree sample holder, but for many materials, or for some materials, this is also not applicable, like for the butterfly wing scale. I mean, this is out of the question. So this was about the missing match artifact. The alignment, we have to think about how to align the tilt series very well, because any misalignment of your tilt series, like shift of those images, would immediately cause some artifacts during the back projection or the reconstruction. And this is how the tilt series intrinsically looks like, and you might think about that there is the tilt axis. These are some marker particles. Depending on the material, you might want to use markers, which you just intendedly attach. This is just gold beads, which are from like a wet chemical solution, and just disperse them onto the surfaces. And you can use those markers to align the sample. You don't have a clear, let's say, contrast features for the alignment. This is after the whole alignment. In this particular case, what Benjamin did is there's software available to just cloak those beams. So we just remove this intensity that is introduced by just assigning some average intensity from adjacent regions. So this is what you might do, but I mean this is like not the perfect way. But in principle, otherwise you might end up with a strong contrast like these golden beams. And depending on your feature size, you know that, like, let's say, it might not be needed. And for sure, you have to think about your contrast mechanism. So the best illumination and imaging conditions for like a specific purpose or specific material and question. And this is, I mean, related to beam sensitivity, because some materials, like organic materials, are far more stable under a parallel electron beam. I mean, it depends like on your features that you're interested in as well, and the sample thickness, and in principle it depends on your field of view that you want to cover in the sample. Let me very briefly talk about the reconstruction. You already saw this slide with a simple Radan transform and back projection. And I mean, I'm not going to spend many slides on that, but what I would like to show you, for this back projection, you can easily imagine that the bigger the sample is, if you tilt to large angles, that your contrast might go down or it might increase. But this doesn't necessarily have to be related to a change, because for instance with stem intensity, it's not perfectly linear with respect to your sample thickness. So meaning that with increasing sample thickness, you might want to weigh your images for the back projection. So you don't use all of them like they are, but you multiply those using a certain factor, for instance. So this is so-called like a filtered back projection. You might apply even filtering. And the quality of this back projection, this is what you might get out of that. So the quality here of the filtered back projection is even better than the simple Radan transformation that I showed in the very early beginning, if you compare that. And it works far better for like incomplete data sets than the simple back projection. And I would just like to spend, let's say, this slide here to show you that instead of using such an analytical solution, I mean, this is what you can calculate. So you calculate your Radan transformation and you apply it to your projections. There are many elaborated techniques. And in principle, I would just point to those which are commonly used nowadays, because I mean, in particular in CT, people want to come up with quantitative data. You know where your like bone is broken, and I mean, if the gap is pretty big, then it's very easy to identify that. But if you have a very fine crack, people want to identify that. So they are still working on like to improve the quality of the reconstructed data for medical applications, for instance. The same holds, I mean, for soft metal use NMR, but in principle, people work on that. This is what is coming up for electron tomography as well. So there are strong advantages. People use this so-called SIRT algorithm, so there are iterative procedures. You use your projections, you reconstruct the volume, you calculate a set of modeled projections, and then you compare them to the original data, and by that you iteratively enhance your reconstruction. So these iterative, let's say, construction techniques, they are also commonly in use. It's called SIRT, and there are like free software tools available to do such reconstruction. One is called IMOD, I-M-O-D. It's pretty good tool, and there was even like a prize awarded a couple of years ago just for the development of all that software and of all this IMOD software package by the European Microscopy Society. And I mean, like there are many, I would say the SIRT and this contrast sensing, this is state of the art for the reconstruction of such data sets. And this is just a comparison of the contrast sensing technique for an incomplete data set. So this is just 130 degrees instead of 180. So we have a missing wedge of 25 or 50 degrees, you know, like 25 in both directions. This is the regular filter plate projection. This is the same, you know, data set used, but this is the result with the compressed sensing technique. So you see that it's far better what you get out of that without adding, like this is just done by can be done by such elaborating techniques. I mean, this resembles far better even for an incomplete data set with a limited tilt angle range what you have. Because I mean, this information, except this very, you know, this very topmost here, what you see, this is still present there. But for the other, you know, directions, this information is in principle included in the tilt data set. But with a simple back projection, you don't utilize that additional information that is present. And so this is why people go for more elaborated reconstruction techniques. In principle, it's nothing else. You need to spend all the effort to record good tilt series, and then you can use all the different ways how to reconstruct the volume. And the last aspect that I want to address before we have our lunch break, the last aspect is atomic resolution tomography. There are different ways. I mean, we saw this tilt series acquisition, you know. There's one example about even to reconstruct the atomic or the distribution of all the atomic species, like the nanoparticles, for instance, by acquiring tilt series. But there are some earlier examples. This is from 2011, where people just recorded stem images along different directions, and they calculated those intensities based on other way. They measured the intensities of each of these atomic columns, and they compared that to models to derive the local number of atoms within those particles here. These are coherently embedded precipitates. To directly correlate the measured intensity with the number of atoms, because we know the scattering impact of an individual atom, we know the scattering impact of a certain number of atoms, and this can only be done, let's say, by modeling, because you need to know like how your intensity works with the local number of atoms, and for these different directions, you locally know the number of atoms, and if you only have two projections, in principle, your 3D distribution of all your atoms is determined. So this is clear. You only need, this is like stereo microscopy. In principle, you only need two directions, and from that you are able to use these local numbers of atoms to calculate the three-dimensional distribution of all your atoms within such a precipitate. So this is called discrete electron tomography. This is stem imaging, because here you can directly relate the local intensity. But this can be done as well by atomic resolution, like high resolution TM imaging. I mean, you just need to know this is an aberration corrected micrograph of a magnesium oxide crystal, where you see all these edges. And you see that there are intensity variations, you know. But based on the assumption that all these atoms are the same, you know that the phase contrast, the local phase, you know, it evolves, the local phase shift depends on the number of atoms along this atomic column. This is an aberration corrected micrograph, so there is no linearization under those conditions, and we can clearly attribute the local intensity again to the local number of atoms at these edges. And so this is how the people came up with the local distribution of atoms here. This is one last example about like a regular tilt series tomography on the atomic scale. So this was done together with the National Laboratory in Berkeley, the Molecular Foundry. And this is also a limited tilt angle range. So this was done on a spot film plus minus 70 dB. And these are all the projections of a lead iron or iron lead particle, and in some directions you nicely see already the projection of the crystal with lattice, like here or in some other directions, just for one tilt axis. after the reconstruction, the people were even able, so this is stated, that people are in principle able to distinguish for the lead-iron system. You might end up with an intermetallic phase with an ordered structure. Like these are slices through the reconstruction with highly ordered areas or highly disordered areas of the alloy, like iron, lead, alloy. And by that people, in principle, people were able to separate those areas where the particle is highly ordered and other areas where the particle is highly disordered, down to the atomic scale. So these are 23,000 atoms. And during this reconstruction, it's pretty elaborated work, so there's important information is like, I don't know, 30 pages or so. They were able to identify at each atomic site the nature of each atom by atomic resolution step immediately. And I mean, this is, like, let's say, quite amazing. This is a very unique experiment because it's already a pretty large particle to do such research. And I mean, I would say this is studied intensively by TM techniques. I mean, you see all these extended effects due to Bragg contrast and strain fields, but there is a lot to learn about materials on the atomic and molecular scale. This has not been widely covered by TM yet, but nonetheless, for many material science applications, this is like including the topography plus the needs that you're going to learn tomorrow. There's like just a vast variety of techniques that you are in principle able to apply for materials. And I hope that I convinced you, in particular Balaji, that it makes sense to some extent to apply electron tomography for material science. I know that this is quite like a new field for most of us, I suppose. But if you have any questions regarding electron tomography, you're highly welcome to address that. So with that, I think we're going to finish for today. Before we leave, I just would like to ask you about which groups are going to attend the TM and SEM.
So this is because, I mean, we had a very smaller group yesterday and we don't want that to be repeated today. So today is 20th and for SEM, today is 20th, that's correct. So today, group 4 is for SEM and for TM, STM it is group 2. That's correct. And in case, for example, if anybody has missed out on the earlier one, and if the present group is not so big, etc., one or two may be considered. No, there is group 4, only that this the last or the bottom right there was a mistake in the sense that here at this place in this group 2 has come at 2 places, so instead of group 1 and 2 it should have been group 1 and 4. That's the only printing mistake, otherwise everything is correct. So we'll do the following things. We'll first learn about the instrument, its various components. Then briefly we will revise at least the important knobs which control the lenses, and after that we will try to understand the microstructure of aluminium. But before that, after having learned this, we will also go through quickly the basic alignment of the microscope. So that will involve like objective lens, we standardize it, then we center the condenser aperture, Z height of the sample, and then followed by objective lens centering and objective astigmatism. So these are the 5 steps. First 3 we do at low magnification, 20K, 40K, like that, and then the last 2 we will do at slightly higher magnification, 100K. Okay. And in the microstructure itself, about the aluminium, it's the same aluminium foil which you might have you definitely have come across packaging foil. So we have prepared, and Ambuj has helped us in preparing that sample. So it's the sample prepared at IUSC. Preparing it is easy because the sample is, the aluminium foil is already 13-14 micron thick. So no need to do any mechanical thinning. Punch a hole, a 3 millimeter disc, and put it into ion milling machine to create a hole inside at the center. Then we already have the sample ready, and it's cheap, no problem, and one can see most of the microstructure features that one would come across any typical sample. For example, we will be able to see grain size, grain boundaries, two beam condition, contrast features like bend contours, thickness fringes, precipitates, dislocation. So almost all that one would usually come across any typical sample is in there also, and therefore is a very convenient sample to learn about microscopy. Since it is still light, and this is a single tilt holder, which means it will only rotate in this manner. Yeah? So this is called as alpha tilt or X tilt, and the sample itself is actually sitting here. At this front part you will see this kind of structure, which is 3 millimeter. Already a TEM grid is inside there. On that they have mounted gold nanoparticles, and they are quite good. So we will learn about that as a next sample. For STEM we might change to this sample. In the case of double tilt holder, there is an additional rotation in this manner also. So like this, this one is done by simply rotating the entire holder, whereas this one, which is not possible in this case, for that they have a more elaborate mechanism, and with that they can tilt it in this direction also. So this double tilt holder is useful for tilting from one zone axis to two beam condition, and if necessary to the next zone axis, etc. So for dislocation analysis we saw that G dot B is equal to 0. So you make images wherein you choose two different two beam conditions and make bright field and dark field images from these two beam conditions, and identify at least 3 G reflections on which the dislocation gets vanished. Then you can identify or calculate the Burbers vector of
So
that.
we can put 4 sample at a time.
Pardon?
One
Sample, only one sample, but there are holders which allow more than multiple samples also, but we don't have them. Okay. So this
sir,
one,
using, let's suppose we want to use only one zone axis, then in which holder we should put our sample, in double tilt or
no, see, any sample if you are interested in tilting, then you have, it is better to use double tilt, because even if you want to have one zone axis also, even then at least you have to go to that first zone axis. Therefore, if you want to do any tilting experiment, then you have to use, it is preferable to use the two beam double tilt holder. So with that I think I will stop with this. So you have got idea as to how a TM sample is and all. And we will proceed with understanding the microscopy cell. So that top unit which you see, 2 feet long unit, that is the gun part. So it will consist of a filament. In this case it is Schottky field emission filament. And then there is an accelerator, so that the electrons which are emitted out of the filament are accelerated to 200 kV. The voltage that is 200 kV is generated in that tank which is in the corner, and that is basically an accelerator. And from there this or high voltage generator, whichever way you call it, and this voltage is then given to the gun. Yeah.
So first we start at a very low voltage.
No, I mean when you are first time starting it, then of course you raise the voltage gradually. That is true. Yes, conditioning, yeah, as they call it. Okay. So after that we have the condenser lens part. The condenser lens part is this much here. And this is the condenser aperture. So it is possible to insert apertures of different sizes. So usually, like for example, now it is the largest condenser aperture is inserted. This is understood by the size of this, and it has to be aligned this. If I want to put or completely take out the condenser aperture, then I turn it like this. This indicates it is completely out. If I just there is a notch system kind of thing. How to center any aperture? Here is one knob and here is another knob. So you will do these alignments, or at least I will do, and you will have a look. So Now it's okay. So this is about the condenser lens part. Then followed by that we have the objective lens, which is in this area. That's the most important part because it creates the first diffraction pattern and first image. And another thing is that so the quality of the image is dependent very heavily on that. And another thing is that many of the important components are very closely in that space, located in that closed space. For example, this is our sample holder. It is actually sitting almost inside the objective lens. And this is the objective aperture, which is sitting just below the sample in the back focal plane. Okay? So this is that. And this is a EDX detector. So here somewhere there must be that silicon semiconductor detector which is able to detect the X-rays. So we have seen how a sample tilt holder is, and this is a double tilt holder, and that's why you see there is wire rotation. For that it is connected via motors. There is a connection for that. So this is for wire. Good. Then this is the selected area aperture. So followed by that we have so-called intermediate lenses and projector lens systems, etc. And this is sitting inside the first intermediate image, selected area aperture. So this plane is conjugate to that of the sample plane, whereas this plane is one of the diffraction planes. Okay, so we have two sets of planes. One is sample and then the image, and then the image, on the screen. So the screen is like this here. This is the fluorescent screen, and when the electrons fall on it, they fluoresce, and that's how we are detecting it. So with the help of our eye and this screen, we will be able to detect. It is also possible to lift that screen up, and there is a CCD camera below. So for digitally storing the images, that can also be done. Okay, so yeah, so I think this is more or less explained. And
So up to here we can use in diffraction mode from that aperture.
which one?
This one.
This is not the diffraction aperture. This is called selected area. Selected area aperture. So that's what we were trying to explain. That we want to select the area of the sample. One way would be that you put your aperture right in the plane of the sample itself.
Yes.
But that would not be practically feasible. So you put it inside the selected area aperture. This is the first intermediate image. So in the image plane you put the aperture. Now the shadow of that aperture will fall on the sample because they are conjugate, they are equivalent planes. When I look at the screen, if I am in the imaging mode, I will see, and if I have inserted the selected area aperture, I can see the aperture also. I can see that it is selecting a particular area of the image or particular area of the sample. So that's why it is called, name is selected area aperture. The name of this is objective aperture, or also called as contrast aperture, because this is the one we use for inducing diffraction contrast. And this is the condenser aperture. With that we can control the convergence angle or the intensity of the beam. Okay. And then these are the two stem detectors. This is the bright field detector and this is the dark field detector. So that will be explained by Professor Benjamin lastly. So I think with that, now we try to, now this is fine that there are lenses and there are apertures and all that, but as such they will be of no use. We should be able to control them somehow. So I will briefly, some of the knobs that we will use, I will explain. This one is heavily used. This is the brightness, it is called, and this is related to the condenser lens. So if you want to have a parallel illumination or focused illumination, we play with this one. Yeah? I will show you also practically in a few minutes. Then the other very commonly used knob is the Shift X and Shift Y. They have a very simple function. They don't do much. They don't change things very much. If there is slight shift in the beam or like that, because that can always happen. These projector lens systems, in that there are some coils are there. They are not there in the upper part of the, I mean this is not, it is only related to some coils which are in the projector lens system or like that. They change so that if the beam has shifted little bit, they will bring it back onto the optic axis. So very simple function of that. Then we have various kinds of coils are there for correcting astigmatism or tilting the beam, etc. Then these are the various, so depending upon what I have pressed, these buttons, they will be, this is like a multifunctional knob, and depending upon which knob I have pressed, they will be assigned. So that there are many. So for example, if one wants to correct the condenser astigmatism, that is my illumination spot, if it is not round for example, then what I will do is I will press this condenser stigmator automatically, then this will get lightened up and these knobs are assigned to the stigmator coils in the condenser lens. So this is how, yes, so this is how the stigmator in the condenser lens is corrected. Similarly, one can do for objective stigmator. Then there is bright field. So with that bright field, one can align the objective axis close to the objective lens. So these are many functions, but this is the general philosophy. Then this one is more or less similar to this, just the other part, or this one. Then we have focus. These are the objective focus, coarse and fine. These are related to the objective lens current, this one. This is standard focus, this is also related to that one. When we press this one, then the objective lens is standardized. That the current in the objective lens is set at a standard value. Then how to change the Z height? Z height can be changed by this Z plus and Z minus. Then there is beam edge wobbler. So it actually makes the tilt in the, it tilts the incident beam, and if my sample is not in the proper plane, then my image will shift from left to right. If that is the case, then I have to understand my sample is not in the proper plane and I have to change its height till the movement vanishes. Eccentric height, actually, technically, yeah, that is the eccentric height alignment, but there are two kinds of eccentric height, or actually, so the proper definition of eccentric height is that when I tilt my sample like this, alpha tilt, then the image shouldn't vibrate. But usually that plane is aligned to the focal plane of the objective lens when the objective lens current has been standardized. So they should match to each other. So right now we are not doing that eccentric height which is determined by the tilting of the goniometer. That we will not do. We assume that it is aligned and equivalent to that of the plane which is defined by the standard lens of the objective lens current. Standard current of the objective lens. So and then we have diffraction focus, which will be related to the diffraction lens current which is flowing, or the power of the diffraction lens, and there are different modes. I was always telling that just by pressing one knob one goes from imaging mode to diffraction mode. So if I press this button, then the diffraction lens is set in such a manner that it will image this particular plane. This is where our first diffraction plane is there. First diffraction pattern is there. If I press on the other hand mag 1, then that lens current is adjusted in such a way that it will image the first intermediate image plane here. So it is very simple that way. Good. I think with that we have more or less got familiar with it, and now we will try to do quickly the alignment.
Sir?
Okay. Yes. Okay. No, not sample temperature. Sample, that would mean that you have a cryo holder. So this is not that. This is, however, it is not cooling the sample itself, but it is cooling the chamber in which sample is there. So this will improve locally the vacuum, and also it will prevent contamination of the sample. And if, for example, something has been coming out from the sample, it will be quickly absorbed by the cold surface around it. So that is it's called anti-contamination device. So first of all, it will prevent the contamination of the sample, and by maintaining better vacuum. So that is by and large the purpose of it. So we are fine. Yeah? So now we will slightly reduce the light and we will proceed with. Okay, so we will now, in order to see the beam, I open the valve. So just to protect the sample, there is a beam valve. So if I press this button, then the illumination has now come. Some valve was there which was blocking the beam, and now the beam is available. I have just aligned the microscope, so I had been to 100K and did the final state, but now we will reduce the magnification to something like 30K. Yeah? And how to move the sample? The movement of the sample is done by this joystick. Yeah? So you can see the sample there. Now let us, for example, now I can still see the sample reasonably, isn't it? Yeah. So yeah.
When we are changing the magnification, that is, we are changing the projector lens current.
Yes. Projector lens current. It might be slightly more complicated also, in the sense that it might not be just one lens. It's a projector lens system or a magnifying lens system. It may change two lens currents or like that. But it is basically right that it is changing the projector magnifying lens current.
सर ये joystick से क्या change हो रहा है? Sample holder movement हो रहा है क्या?
नहीं sample location. Sample holder का अंदर से थोड़ा बहुत movement हो रहा है. Yeah, that is correct. X and Y is done here, and with this tilt, that is the X tilt. Yes, that is true. Okay. So now we are seeing the beam also, and I can put it slightly away. Right now I am in vacuum. So if I will decrease the magnification still further, then maybe we can even see. Yeah. So now you can see more or less how this is the hole in the sample. Yeah. So I mean, yeah, 6,000 is 6,000 से नीचे भी जा सकते हैं मनु थोड़ा. हाँ थोड़ा सा. नहीं तो low mag पे आप जा. हाँ नहीं, you will not go to low mag. So you can see that this is how the hole is, and hole is looking bright in this case. Yeah. So fine, good. Then I will again go to slightly higher magnification, and I can adjust the illumination with this knob, condenser brightness knob. Yes. And so that's how it is looking. So our first step, we said that we will press this button. So our objective lens is standardized, and we are at 10K. We'll go to slightly higher magnification, at least 20K. So 25K should also be, let's say. And it has become less intense. So I will adjust the current in such a way that it is like now. And just check also which aperture is there. Right now it is the highest or the biggest aperture. So yeah, and so this was the first step. The second step was that we wanted to align the condenser aperture. So if I now focus it, then it is coming to the center of the screen. So if you at the center of the screen you see some black spot. It's actually a hole. So that is where it is coming and converging. So see, it has come to that. There is slight shift, but that shift is more or less minimal. But we will maybe how to bring it to the center is that with this shift.
So this is beam shift.
This is yeah, you are right. So this. So this is let us check. Yeah, this is beam shift. Correct. Okay, so we have come to.
सर लेकिन आपने कौन सा प्रेस किया है? ऑब्जेक्टिव वाला कौन सा प्रेस?
नहीं, मैंने अभी यहाँ पे कोई नहीं प्रेस किया है. तो ये जो स्टेप है ना, ये बीम शिफ्ट वाली जो स्टेप है, वो बाय डिफॉल्ट उसका काम यही रहता है. उसको कोई असाइन करने की जरूरत नहीं. ओके. ऑल राइट. हाँ, ओके. So I will try my best to do most of the steps on the screen so that most of you can see. But right now it is very simple, so it is not very big deal. So you see now it is more or less symmetric. Yeah. What I can do is I can misalign the sample condenser aperture and try to align it. So I will not do it too much because doing too much may put us in trouble. But little bit I will do, and let's see what will happen. So I have misaligned it little bit, yeah, and let us see what happens when I focus it. It indeed is at the center by and large, yeah. But when I go over focus, it is going in that direction. when I bring it to focus and go in the other focus, then it is going in that direction. This is how you should identify that there is misalignment of the condenser. Now how to correct it? First is go to focus and see that it is indeed at the center. If it is not at the center, then using these shift knobs you bring it to the center. Now I then go to overfocus. In the overfocused or defocused, let us say, in the defocused condition, if it is going away, that has to do with the condenser aperture. So I will try to bring it in the center. And when I do this correction, I make this correction in a, like I don't correct it 100%, I correct it 90%. Why? Because I have also to try to go in the defocus of the other direction. So I will now go in the defocus of the other direction and correct little bit from that side also. In 2-3 iterations, things become more or less audible. So I will make some correction. So I would assume that now this should be fine. So there is little bit of shift that happens always. That's why, I mean, this step is so commonly used, so that one has to keep on doing whenever we are doing the microscope. That is like constantly one should keep on doing it. That's not a problem. So now our condenser aperture is aligned. So 2 steps we have done. Now what remains is the Z height of the sample. So for that we have, till now we were not requiring the sample. Now we have to find it. But we know, I mean, this is the sample, and these are the this is the sample. Okay. So there is a sharp region also. Having a sharp edge is better. So right now I think I can already bring the this thing on the screen. So you can now go back actually, all of you, so that it becomes easy for everybody. So and then, so now the screen will lift up. The camera is on, isn't it, Manu? Camera? Okay, we can do that later also. So yeah, it is already on. Yeah. So this was one sharp edge in the sample which I have put it here. You can see some Fresnel fringe there. That is because we have not done the Z height alignment. It is still in, I mean, our sample is not in correct focus. That is one indication. The other indication, I mean, there are many ways in which one can do. Now we want to do the Z height. So there are multiple ways. One way is that I just look at the, I see that there is some contrast already. Yeah? One can minimize that contrast and one will be in the focus. If I try to adjust the Z height in such a way that this fringe vanishes, that is also one way of doing it. Other way of doing it is that you, this Wobbler X. So what it does is it changes the current from like the beam tilt of the, it changes from like, it vibrates the beam. Now if the sample were at the correct position, then this changing should not move the sample. But if it is not at this correct position, but it is somewhere here, then it will start to image different regions of the sample, and so it appears that the sample is moving. So we will do by, let us say, this which is given here, but let us see. Yeah, so I have started the image wobbler and you see it is vibrating. So now we will try to minimize that, and these are the buttons Z plus. So yeah, it has become slightly better. So I will do it little more, and is now much better, isn't it? And also the fringe has also vanished. Correct? So I think we should be satisfied with that. So I removed that wobbler. So now it is like this. There is some faint is there, faint fringe type of thing is there. That is alright. And also as a general rule, whenever you acquire an image, you always try to acquire with slightly under focus. So this is the objective focus. You should acquire it in such a way like this maybe, or little less, but some white, a tiny white fringe, because that it gives better contrast. Now this is looking, let's say I have done it little more. This is looking much more clear than when it was in the focus condition. So you don't acquire images with exactly at the correct focus, but slightly under focus, so that this white fringe, slight white fringe is there, and it gives better contrast. Alright. But that was not actually the intended step that we want to do. That was some extra thing that I just told you. Okay. So we have adjusted the Z height. So now what we will do, we will go to higher magnification, and we want to now do the objective lens centering. Okay. So we have now, first of all, we set the objective lens at a proper current, so that we are defining one plane. and then we aligned the condenser aperture on the optic axis of the microscope, and after that we have put the sample in the correct height, and now we want to ensure that, let's see if the objective lens is on the correct optic axis or not, or if it is tilted to the optic axis. If it is tilted, then when I change the high voltage, then if I change the high voltage, then effectively I am changing the power of the objective lens, because for 200 kV the objective lens will have one particular focal length, but if I use 120 kV it will have another focal length. Now that is exaggeration. If from 200 kV I change it by plus minus 10 kV, then it is as if I am continuously changing the magnification of the objective lens. Now if my sample was, if the objective lens was or the axis of the objective lens was parallel or aligned on the optic axis of the microscope, then this change in magnification should only result in making my image look smaller or bigger, because the magnification I am effectively changing of the objective lens. But if the axis of my objective lens is slightly like this and not like this, then it will make the image to vibrate again, because it will magnify in a it will change. So that's why it is not in the optic axis, is not in the center. So there will be some ascent. We will see how it looks like. So I have to now, that is called a high tension wobbler, and I have started it, and you see that it is slightly, there is slight movement, but it may not be slight. So what I will do is I will misalign it little bit so that we can correct it later. So what I do is I go to bright tilt here. So as you can see, tilt means I am trying to tilt a little bit the optic axis of the objective lens, and with this deflection, now the lower ones, I will make it just, we'll do both. I mean, we'll try to correct it, we'll change it somehow, and let's see how it works. So now you see there is more movement. It has become worse. Yeah? The movement has become even worse. So right now my optic axis of the objective lens is not aligned to that of the microscope. So now we will correct this effect. Keep looking there so that we should get minimum movement. That's the aim. So I am trying to correct it. Okay, now I get a feeling that it has started to move in one direction, so I come to the other one and try to make it as minimum as probably, this is probably the wrong direction, so I reverse. Yeah, something like this. Maybe one can try again. So it's just this is the process. I mean, whenever you have access to the microscope, you can always try it. But this is the simple process. So this looks pretty fine, isn't it? So I stop the high tension wobbler. So now unless you change the objective lens current is not dependent on the sample at all. That is, when you change the focus of the objective lens, then it will change. So just since he has asked the question, let me clarify. The process of focusing the sample is like this, that we set the objective lens current to the standard value, and ideally one should never have to change that objective lens current, because that's what we said, we'll keep it fixed. That's our reference. Yeah, you are right. I'll explain your issue also. So then we do the Z height alignment using the mechanical these knobs. So the sample position is changed. But the trouble is that this mechanical alignment of the Z is not so fine. We can only up to a certain level we can do this Z alignment. It will still be slightly defocused or out of that exact plane on which it should have been. Now this final tuning is done by, again, rather than changing the Z height, we change slightly the focus of the objective lens itself. So it is not, ideally it shouldn't be done, but in practice that's what is followed. So now we have done the fourth step also. which was objective lens centering. That we have done. Now we have to see about the objective lens astigmatism, and that there are two ways of looking at it. One is you already see that there is some fringe here, but if I look at it more carefully, I can see that this fringe is slightly inhomogeneous, in the sense that from the top part it is probably less bright, whereas from the bottom side it is more bright. Correct? Okay, so which means there is some inhomogeneity. So one should have, that is the indication that there is some objective astigmatism, etc. But it also depends upon which objective aperture you have put in and like that. And for the normal diffraction contrast microscopy, this may not be that relevant also. I mean, it need not be so very correct, so very properly aligned. But we may still, nonetheless, let us try to see the effect of focus on the fringe pattern which is coming. So this is objective focus. I will try to go in, now you see I am going to the under focus, that is I am reducing the current in the objective lens, and I get this bright fringe which has become stronger. I will reverse the direction, that is I am making my lens stronger and going closer to focus, and then this is where is my more or less the focus. And if I further go in the other direction, then the dark fringe begins to appear. But this dark fringe also, as you can see, is probably not entirely homogeneous. That inhomogeneity in the strength of the intensity of the fringe, that is the indication of astigmatism. We will not probably correct it, or so if we want to correct, then one has to go to objective stigmata. Once I press that, then this bright field has gone, automatically it goes there. And now we will, using these deflection stigmata knobs, one can try to correct it, for example. So let's do, if it helps a little bit. Okay, so this is one way of doing it. The other way of doing it is you try to have some amorphous sample. Carbon foil, for example, or this stem grade, it has lacy carbon film, that's amorphous. So on that you acquire the Fourier transform, FFT of the images live. Then you get so-called FFT, fast Fourier transform, and that will show circular rings. If there is astigmatism in the objective lens, then it will show not circular FFT, but some preferential direction, it will be elliptical. So that you have to eliminate. From elliptical, you make it as circular by changing these knobs here. Okay?
Sir, we can also do the FFT in this sample. If near to the ore there is some
amorphous. Yes, but I mean it will be still like you need to take an image of the whole image should be filled with amorphous region. Now there will be some interference due to the crystalline structure which is there. So that's why it may not be that ideal. But when we are doing the nanoparticle samples, there will be amorphous film. That time it can be displayed also. Okay. So this is too much black. I will try to reduce and then let us see. Yeah. Okay. So I would say that this is how typically the microscope is aligned. Okay. So now we want to study the next. So we are done with the alignment, and now we want to study the microstructure. So what we can do is